Welcome to the Late Lab. I'm very glad you're here. Before we settle into tonight's little corner of reality, I'd love to know where you're watching from. Maybe you're tucked away in bed, half listening in the dark. Maybe you're on a quiet sofa, with the room lit only by a lamp. Or maybe you're somewhere between awake and asleep, letting the day slowly loosen its grip. Wherever you are, I hope you're warm, comfortable, and ready to let your mind wander gently toward the smallest edge of space itself. If you enjoy these calm journeys through science, a like and subscribe really does help this sleepy little laboratory keep its lights on. And if you're already here often, thank you, truly. It means a great deal to have you drifting through these ideas with me. Tonight, I'll do my best not to make the smallest possible length in physics sound too dramatic. Although, to be fair, when a distance is so tiny that ordinary space may stop behaving like space, it is rather hard not to raise an eyebrow. Just one eyebrow, though. We're trying to stay relaxed. So let's begin, shall we? What is the Planck length? And could it be the smallest length reality allows? The smallest length reality allows is not a phrase that physics can answer quite as simply as it first appears. It sounds as though, somewhere, far beneath atoms and particles and all the familiar furniture of the universe, there might be a final little brick of space, a tiny square on the cosmic screen, the last possible notch on nature's ruler, and below that, nothing smaller can exist. That picture is tempting. It is also not quite what scientists mean when they talk about the Planck length. The Planck length is better understood as a boundary of meaning. It is a scale so small that our best existing theories begin to lose their ordinary grip. It may be a lower limit to meaningful distance, or it may be a signpost pointing toward a deeper theory of quantum gravity. But it has not been proven to be a literal pixel of space, or a tiny grain that reality is definitely made from. Physics, being wonderfully inconvenient at times, refuses to hand us the simple version just because it would fit nicely on a thumbnail. To feel why this matters, it helps to begin with the sizes we can almost imagine. A human being is usually measured in meters, a hand in centimeters, a strand of hair in fractions of a millimeter. With a microscope, the world opens downward into cells, bacteria, and the delicate structures inside living things. Go smaller again, and we reach atoms, those tiny arrangements of electrons around dense central nuclei. An atom is roughly a 10 billionth of a meter across. Depending on the atom and how it is measured, that is already far smaller than anything our senses were built to understand. Inside the atom is the nucleus, smaller again by about a factor of 100,000. And inside many nuclei are protons and neutrons, made of quarks and gluons, held together by the strong nuclear force. A proton is roughly 1/4,000,000th of a meter across. That is an astonishingly small distance. If an atom were expanded to the size of a cathedral, its nucleus would still be more like a tiny insect drifting somewhere near the centre. A proton would be smaller still, hidden inside that already tiny centre. And yet the Planck length is not merely smaller than a proton, it is smaller by around 20 orders of magnitude. That means a proton is to the Planck length roughly what a large everyday distance is to something almost unimaginably tiny. The comparison starts to break the mind a little, so please do not worry if your imagination quietly leaves the room and makes itself a cup of tea. The Planck length is approximately 1.6 times 10 to the minus 35 meters. Spoken out, that is 0 point followed by 34 zeros and then a 16 in meters. It is so small that if you tried to compare it with the width of a human hair, the difference would be absurdly greater than the difference between that hair and astronomical distances. It does not belong to the world of microscopes. It does not even belong to the world of particle accelerators in any direct practical sense. It belongs to the place where quantum mechanics, gravity, and space-time all seem to meet. The name comes from Max Planck, the German physicist whose work on blackbody radiation helped open the door to quantum theory. Around 1900, Planck found that the behavior of glowing hot objects could be explained if energy was exchanged in discrete amounts rather than in a perfectly smooth flow. This idea brought into physics a new constant, now called Planck's constant. It became one of the central quantities of quantum mechanics, setting the scale at which the universe begins to behave in ways that are very unlike ordinary classical physics. The Planck length is built from three constants: the speed of light, Newton's gravitational constant, and the reduced Planck constant. Each one belongs to a different great region of physics. The speed of light belongs to relativity and tells us how space and time are connected. Newton's gravitational constant belongs to gravity and tells us the strength of gravitational attraction. The reduced Planck constant belongs to quantum mechanics and tells us the scale of quantum effects. When these three constants are combined in the right way, they produce a length. Not just any length, but a natural length formed from the deepest ingredients of the theories we already have. In clear spoken form, the relation is the Planck length equals the square root of the reduced Planck constant multiplied by Newton's gravitational constant, divided by the speed of light cubed. That may sound like a very elegant recipe for something impossibly small. A pinch of relativity, a spoonful of gravity, and just enough quantum mechanics to make the whole kitchen nervous. But the meaning is profound. The Planck length appears where the rules of quantum theory and the rules of general relativity can no longer be safely kept apart. Classical mathematics allows space to be divided endlessly. A line can be cut in half, then half again, forever. There is no final mathematical point at which the process must stop, but physics has to ask a different question. Not just whether a smaller distance can be written down, but whether it can be measured, probed, or given physical meaning. That is where the mystery begins. To explore smaller distances, we need higher energies. But energy also gravitates. At extreme enough scales, trying to look more closely may disturb space-time itself. The ruler becomes part of the thing being measured. The act of probing reality may create the very limit we're trying to pass. So the Planck length is not simply the discovery of a tiny cosmic tile, it is the edge of a map drawn by our current theories. On one side, space and time behave smoothly enough for relativity to describe planets, stars, black holes, and the expanding universe. On another, quantum mechanics describes atoms, particles, fields, and probabilities with astonishing precision. But at the Planck scale, both languages are needed at once, and there, at the smallest length we can sensibly name, reality seems to whisper that our usual idea of distance may not go on forever. For most of the history of physics, space was treated as something beautifully simple. It was the quiet stage on which everything happened. Matter moved through it, light crossed it, planets traced paths inside it, apples fell through it, which was unfortunate for the apple, but very useful for science. In this older picture, space is smooth and continuous. That means there are no obvious breaks, gaps, grains, pixels, or final little blocks. Between any 2 points, however close together, mathematics allows another point to be placed. Between those two, another again. And then another. Space, in this sense, can be divided forever, at least on paper. This was the world of classical physics. It was the world in which nature seemed to behave like an enormous, elegant machine, with positions, velocities, forces, and motions all unfolding in a definite way. If you knew where every object was, how fast it was moving, and what forces acted on it, you could, in principle, calculate what would happen next. Isaac Newton gave this picture one of its most powerful forms. In Newton's view, space and time were absolute. Absolute space existed independently of the objects inside it. Absolute time flowed evenly, everywhere, whether anything was happening or not. The universe could be imagined almost like a vast, invisible room, with a perfectly steady clock ticking in the background. This may sound slightly old-fashioned now, especially after Einstein gently walked in and rearranged the furniture. But Newton's picture was not foolish. It was extraordinarily successful. It explained falling objects, cannonballs, tides, pendulums, and the orbits of planets. It allowed human beings to understand the motion of the moon, the paths of comets, and the structure of the solar system with a precision that was, for its time, almost magical. The mathematical language beneath this picture was Euclidean geometry, named after the ancient Greek mathematician Euclid. Euclidean geometry describes flat space using points, lines, angles, surfaces and distances. A point has no size, a line has length but no thickness. A plane stretches out smoothly. These are ideal objects, not things you find lying around in a cupboard, unless you keep a very unusual cupboard. But as ideal tools, they are incredibly powerful. They allow space to be described with exactness. A point can mark a location. A line can connect 2 points. A distance can be measured between them. A shape can be rotated, shifted, stretched, or compared. In ordinary life, and even in much of astronomy, this smooth geometric picture works so well that it feels almost obvious. When you walk across a room, you do not notice space arriving in chunks. Your hand does not jump from one position to another like a badly animated cartoon. A rolling ball appears to pass through every position along its path. A planet orbiting the sun does not seem to hop from one invisible cosmic square to the next. Motion looks continuous. Space looks smooth. Time seems to flow. To describe this smooth motion, Newton and Gottfried Wilhelm Leibniz developed calculus. Calculus is the mathematics of continuous change. It allows physicists to describe velocity as the rate at which position changes, acceleration as the rate at which velocity changes, and curved motion as something that can be analysed moment by moment. It turns the flowing world into equations that can actually be worked with. This was a tremendous achievement. Calculus made it possible to describe not just where something is, but how it changes as time passes. It gave physics a way to handle slopes, curves, falling bodies, planetary paths, waves, and countless other processes that do not happen in neat little steps. Classical physics became a science of smooth variation, and for the world we usually experience, this is exactly what is needed. A bridge does not require quantum gravity to stand up. A train timetable does not need the Planck length, though it may need some kindness from whoever designed the delays. A spacecraft travelling to Mars can be guided mostly with classical mechanics, plus relativistic corrections where needed. For almost every familiar purpose, treating space as continuous is not just convenient, it is astonishingly accurate. This is because, if reality has any deeper grain, it lies far beneath the scales where classical physics usually works. A meter can be divided into centimetres, millimetres, micrometers, nanometers, and smaller units still. Atoms themselves are tiny compared with everyday things, yet even atoms are enormous compared with the Planck length. The possible boundary we are concerned with is not hidden just below the surface of ordinary life. It is buried so far beneath it that ordinary language begins to creak. The important point is that classical physics does not contain an obvious stopping point. There is nothing in Euclidean geometry that says a line can only be divided a certain number of times. There is nothing in Newton's original picture of absolute space that says distance must come in indivisible pieces. Mathematically, smaller and smaller lengths remain perfectly acceptable. A millionth of a meter, a billionth, a trillionth, and on and on. The symbols are quite happy to continue even if the human imagination has gone for another cup of tea. But physics is not only mathematics, it is mathematics tied to nature. A distance is not just something we can write down. It is something we may want to measure, probe, compare, or use in a physical prediction. And this is where the smooth classical stage begins to meet its deepest question. If space can be divided endlessly in mathematics, does nature itself allow endless division? Can every smaller length still have a clear physical meaning? Or is there a scale where the idea of distance stops behaving like the simple concept we inherited from geometry? The Planck length is strange not merely because it is small. Physics contains many small things, and most of them are already rather humbling. The Planck length is strange because it challenges the assumption that the question what happens at an even smaller distance can always be asked in the same way. It suggests that below a certain scale, the smooth stage of classical space may no longer be the right picture. Classical space is calm, continuous, and beautifully useful, but it may not be the final foundation. It may be an excellent large-scale description, like the smooth surface of water seen from far away. Only when we look unimaginably closely do we begin to wonder whether smoothness is the truth of reality, or simply the way reality appears before the smaller scales are allowed to speak. A distance is easy to imagine when it belongs to ordinary life, the width of a table, the length of a garden path, the space between your hand and a cup of tea, which may become the most important distance in the universe at certain times of night. But in physics, distance is not only an idea in the mind, it is something that must be established physically. To say how far apart two things are, we need some way of comparing them. We may use a ruler, a beam of light, a clock, a detector, or the behavior of particles. Measurement is not magic. It is an interaction between the thing being measured and something else. At everyday scales, this is easy to forget. A ruler can be placed beside an object without changing the object very much. A tape measure does not normally disturb a room. A surveyor can measure a field, and the field does not become offended and rearrange itself. But as physics moves downward into smaller and smaller distances, measurement becomes less passive. Looking closely is not just looking, it is doing something. The basic problem is resolution. To see a small detail, the tool used to examine it must be sensitive to that detail. With light, this is tied to wavelength. A long wavelength cannot easily reveal structures much smaller than itself. It washes over them, rather like a large ocean swell passing over tiny ripples. To resolve smaller features, we need shorter wavelengths. This is why ordinary visible light microscopes have limits. Visible light has wavelengths of a few hundred nanometers, so it can reveal cells and some structures inside them, but it cannot cleanly resolve individual atoms. That is not because the microscope is badly behaved or has failed to eat its vegetables. It is because light itself has wave properties, and those wave properties set a boundary on what can be distinguished. The wave nature of light became clear through the work of many scientists, but James Clerk Maxwell gave it one of its greatest forms in the 19th century. Maxwell showed that electricity and magnetism are united in electromagnetic waves, and that light itself is one kind of electromagnetic wave. In this view, light is not simply a stream of brightness moving through space. It has wavelength, frequency, and field-like behavior. The same kind of surprise later appeared for matter. In the early 20th century, Louis de Broglie proposed that particles such as the electrons also have wave-like properties. This idea, matter waves, became one of the foundations of quantum mechanics. An electron is not just a tiny solid pellet travelling like a microscopic marble. It has a wavelength associated with its momentum, and that wavelength affects how it behaves. This opened a new way to probe smaller distances. Electrons can have much shorter wavelengths than visible light, especially when they are accelerated to high speeds. Electron microscopes use this fact to reveal structures far smaller than ordinary light microscopes can show. They do not simply make a better glass lens, they use a different physical probe. The same principle continues in particle physics. To investigate the smallest known structures, physicists do not build a microscope with a comically large magnifying glass. They accelerate particles to enormous energies and collide them, then study the patterns of particles that emerge. Higher energy corresponds to shorter effective wavelengths, allowing smaller scales to be explored. The European Organisation for Nuclear Research, known as CERN, is one of the great centres of this work. Its Large Hadron Collider accelerates protons around a ring roughly 27 kilometers in circumference before smashing them together at extremely high energies. These collisions helped reveal the Higgs boson, announced in 2012, and continue to test the standard model of particle physics with remarkable precision. But even the Large Hadron Collider is nowhere near the Planck length. It explores distances incredibly small by human standards, roughly around a 10,000th of a proton's width in some interactions, depending on how the scale is described. Yet the Planck length is still enormously smaller. It lies far beyond what present accelerators can directly probe. The reason is not only technological, it is conceptual. To explore shorter distances, we generally need higher energies, but energy is not harmless. In quantum theory, it helps sharpen our view. In relativity and gravity, energy also contributes to gravitational effects. Energy can curve space-time, and if enough energy is concentrated into a sufficiently tiny region, gravity can no longer be ignored. This is where the innocent idea of measurement begins to change. At larger scales, adding more energy gives a clearer picture. At smaller scales, especially as one imagines approaching the Planck length, adding energy may begin to disturb the very stage on which the measurement is supposed to happen. The probe is no longer just revealing space, it may be affecting space-time itself. So measuring smaller and smaller distances is not like zooming in forever with a perfect camera. There is no silent, invisible lens that can inspect reality without touching it. Every measurement uses something physical. Light scatters, electrons interact, particles collide, detectors absorb energy, clocks tick through space-time. The act of knowing has a physical cost. This does not mean reality is vague in a lazy or mystical way. It means that the rules of nature are stricter than everyday intuition expects. At ordinary scales, measurement can feel detached. At quantum scales, measurement becomes part of the story. And near the Planck scale, the story may include gravity in its most difficult form. The Planck length appears then, not merely as a tiny distance, but as the place where measurement itself becomes uncertain in a deeper sense. To ask what lies below, it may require a probe so energetic that the question stops behaving like a normal question about distance. Instead of uncovering a smaller feature, the attempt may bend, blur, or even hide the region being examined. Smaller is not always simpler. Sometimes going smaller means carrying more energy, creating more disturbance, and forcing more of physics to take part. And at the smaller scales we can sensibly imagine, the universe seems to make one thing quietly clear. A ruler is never just a ruler when space-time itself begins to tremble. The first crack in the smooth picture of reality did not arrive as a dramatic explosion, or a telescope peering into a strange galaxy, or a particle accelerator discovering something with a deeply inconvenient name. It arrived through heat. More specifically, it arrived through the problem of blackbody radiation. A blackbody is an ideal object that absorbs all radiation falling on it, and then emits radiation according to its temperature. Real objects are never perfectly ideal, because nature is rarely interested in helping our diagrams behave. But many heated objects come close enough for the idea to be extremely useful. When something becomes hot, it glows. A piece of metal warmed in a fire may first glow dull red, then orange, then yellowish white, as the temperature rises. The colour changes because the pattern of emitted radiation changes. Hotter objects emit more energy overall, and the peak of their emission shifts towards shorter wavelengths. In the late 19th century, physicists wanted to understand this pattern using classical physics. They had thermodynamics, electromagnetism, and the idea of smooth energy exchange. These tools had worked beautifully in many areas. It seemed reasonable to expect that heated radiation would also fit into the same continuous picture. But it did not. The observed spectrum of black-body radiation had a very specific shape. At long wavelengths, classical theory could do reasonably well, but at short wavelengths, especially in the ultraviolet region, the predictions went badly wrong. Classical reasoning suggested that a hot object should emit more and more energy at shorter and shorter wavelengths, without a sensible limit. If that were true, ordinary heated objects would pour out an absurd amount of ultraviolet radiation. This failure became known as the ultraviolet catastrophe. It is an excellent name, partly because it sounds like a small disaster involving a very dramatic lamp. But the problem was serious. It showed that classical physics, with its smooth distribution of energy, could not explain what nature was actually doing. Max Planck confronted this problem around 1900. Planck was not trying to overthrow physics for fun. He was trying to solve a technical puzzle about radiation. But in doing so, he introduced an idea that would quietly change everything. Planck found that the observed blackbody spectrum could be explained if the energy exchange between matter and radiation did not vary in a perfectly continuous way. Instead, it had to come in discrete amounts. These amounts depended on frequency. Higher frequency radiation involved larger packets of energy, while lower frequency radiation involved smaller ones. The relation can be spoken simply as energy equals Planck's constant multiplied by frequency. Planck's constant became one of the deepest numbers in physics. It's extremely small in everyday units, which is why ordinary objects do not usually appear quantum in an obvious way. A football does not drift around like a probability wave, at least not unless the match is going very strangely. But at atomic and subatomic scales, Planck's constant sets the size of quantum effects. It tells nature where the smooth assumptions of classical physics begin to fail. At first, Planck himself treated this idea with caution. It was, in part, a practical mathematical step. He had found a way to match the data. But the meaning of that step was far larger than it first appeared. Energy was not behaving like a perfectly smooth fluid. At the deepest levels, it seemed to arrive in countable portions. Then, in 1905, Albert Einstein pushed the idea further. He used the quantum idea to explain the photoelectric effect, where light shining on a metal surface can knock electrons out of it. Classical wave theory had difficulty explaining the details. Increasing the brightness of low-frequency light did not necessarily eject electrons, while high-frequency light could do so even at lower intensity. Einstein proposed that light itself behaved as if it came in individual quanta of energy. These light quanta were later called photons. The energy of each photon depended on its frequency, following the same basic relationship Planck had introduced. Higher frequency light carried more energy per photon. If each photon had enough energy, it could free an electron from the metal. If it did not, then simply adding more low-frequency photons would not solve the problem. This made the quantum idea more physically direct. It was not merely a clever mathematical trick for heated objects. It suggested that radiation itself had a graininess of a strange new kind. Light still had wave properties, as James Clerk Maxwell's electromagnetic theory had shown, but it also behaved in particle-like packets when exchanging energy. This was one of the great turning points in modern physics. Classical continuity was not destroyed all at once. It remained useful and powerful across enormous ranges of experience, but it could no longer be treated as the final rule of nature. Energy, light, and matter were beginning to reveal a structure that classical physics had not expected. The link to the Planck length comes through Planck's constant. Once physics had a fundamental quantum scale, that scale could be combined with other fundamental constants. The speed of light connects space and time through relativity. Newton's gravitational constant sets the strength of gravity. Planck's constant sets the scale of quantum behavior. Bring these together, and a natural length appears. This length is not invented by choosing a human unit, like a meter or an inch. It emerges from the constants at the foundations of our theories. It is the Planck length. That is why Planck's work on blackbody radiation matters so deeply here. The question of the smallest meaningful length did not begin with someone slicing space into tiny pieces. It began when physics discovered that smoothness itself was not always reliable. Energy had a quantum scale, light had quantum behavior, matter would soon reveal waves, probabilities, and uncertainty. The Planck length is a later echo of that first crack in continuity. It asks whether space and time too might have a limit where the old smooth picture no longer works. Max Planck did not solve quantum gravity in 1900, but he opened the door to the possibility that nature is not continuous all the way down, and once that door was open, the smallest length reality allows became a question physics could no longer ignore. The Planck length was not found by placing a tiny ruler against the universe and squinting very carefully. No experiment has directly measured a little mark in space and announced, with suitable scientific politeness, that this is where length finally stops. The Planck length comes from something stranger and in some ways more beautiful. It is constructed from three constants of nature. A constant of nature is a number that appears to belong not merely to one object, one material, or one place, but to the structure of physical law itself. The Planck length is built from the speed of light, Newton's gravitational constant, and the reduced Planck constant. Each of these constants carries a deep piece of physics with it. One speaks the language of relativity, one speaks the language of gravity, one speaks the language of quantum mechanics. The first is the speed of light. In empty space, light travels at approximately 299,792,458 meters per second. This is not just the speed of something bright moving quickly. In Albert Einstein's special relativity, introduced in 1905, the speed of light is a fundamental limit woven into the relationship between space and time. James Clerk Maxwell had already shown in the 19th century that light is an electromagnetic wave. His equations joined electricity and magnetism into one theory, and they predicted waves moving at a particular speed. That speed matched the measured speed of light. This was one of those moments in physics where the universe seems to lean over and whisper, yes, these things are connected. Einstein then took the speed of light even deeper. In special relativity, all observers moving at constant speeds measure the same speed of light in a vacuum. This strange fact changes how space and time behave. Distances can contract, durations can stretch, simultaneity becomes relative. The speed of light becomes the conversion factor between space and time, showing that they are not two entirely separate stages but parts of one structure. The second ingredient is Newton's gravitational constant. This constant appears in Isaac Newton's law of universal gravitation, published in the late 17th century. Newton showed that every mass attracts every other mass, and that the strength of the attraction depends on the masses involved and the distance between them. Newton's gravitational constant tells us how strong that attraction is. Gravity is incredibly important on large scales. It shapes planets, stars, galaxies, black holes, and the expansion of the universe. Yet compared with the other fundamental interactions, gravity is astonishingly weak. You can lift a small object from a table with your hand, overcoming the gravitational pull of the entire Earth. This is a nice confidence boost for the hand, although perhaps less flattering for gravity. But gravity never really disappears. It acts on mass and energy. At ordinary particle scales it is usually so weak that it can be ignored, but near the Planck scale this changes. If enough energy is concentrated into a tiny enough region, gravity becomes impossible to leave out. That is why Newton's gravitational constant belongs in the construction of the Planck length. The third ingredient is the reduced Planck constant. This is closely related to Planck's constant, the quantity introduced through Max Planck's work on blackbody radiation. In quantum mechanics, the reduced Planck constant appears naturally in many of the theory's deepest relationships. It is found in angular momentum, wave functions, uncertainty relations, and the mathematics of quantum states. The reduced Planck constant sets the scale of quantum behavior. It tells us why atoms do not behave like tiny solar systems governed only by classical mechanics. It helps explain why electrons occupy quantum states, why matter has wave-like properties, and why there are limits to how precisely certain pairs of properties can be known at once. It is one of the quiet signatures of the quantum world, so the Planck length combines three ideas. The speed of light brings in relativity and the structure of space-time. Newton's gravitational constant brings in gravity and the curvature or attraction associated with mass and energy. The reduced Planck constant brings in quantum mechanics, and the fact that small-scale physics is not continuous in the old classical sense. The method used to combine them is called dimensional analysis. This means looking at the units carried by each constant and asking how they can be arranged to produce a particular kind of quantity. A length has units of distance. The speed of light carries distance and time. Newton's gravitational constant carries information about gravity, mass, distance, and time. The reduced Planck constant carries energy, time, and quantum action. When these constants are combined in exactly the right way, the units simplify into a length. The spoken equation is the Planck length equals the square root of the reduced Planck constant multiplied by Newton's gravitational constant divided by the speed of light cubed. This may sound like a recipe written by a very serious baker with a suspicious interest in space-time, but the result is not arbitrary. It is a natural scale. It does not come from human body parts, like feet. It does not come from Earth size, like early versions of the meter. It comes from constants that appear to belong to the deep structure of physical law. That is why the Planck length matters. It is not simply a tiny number pulled from the air. It is the length produced when quantum mechanics, gravity, and relativity are forced into the same sentence. And that is exactly what must happen when we ask about space-time at its smallest meaningful scale. For most familiar physics, these three ideas can often be handled separately. Relativity explains fast motion and strong gravity. Quantum mechanics explains atoms and particles. Newton's gravity still works beautifully for planets, spacecraft, and falling objects when conditions are not too extreme. But the Planck length marks a scale where separation may no longer be allowed. At that scale, quantum uncertainty, gravitational strength, and the structure of space-time all become part of the same problem. The Planck length is therefore not only a measurement of smallness, it is a meeting point. It is where three great pillars of physics touch, and where our current understanding begins to feel the pressure of something deeper underneath. The Planck length is so small that it almost refuses to be pictured. Some tiny things can still be brought within reach of imagination with the right comparison. A grain of dust, a cell, a molecule, an atom. Even a proton, although far beyond direct human sight, can at least be placed somewhere on a mental ladder of smallness. The Planck length sits so far below that ladder that the ladder itself begins to look rather optimistic. Its value is roughly 1.6 times 10 to the minus 35 meters. Spoken more slowly, that is a decimal point followed by 34 zeros, and then the digits 1 and 6. It is not just small in the way a speck of pollen is small, or a virus is small, or even an atom is small. It is small compared with the things that are already unimaginably small. An atom is usually around 1/10 billionth of a meter across, depending on the element and how its size is defined. That already places atoms far beneath ordinary sight. If you could line up 10 billion atoms across a meter, you would have a sense of how tiny each one is. Inside the atom is the nucleus, about 100,000 times smaller than the atom itself. And inside many nuclei are protons and neutrons, each with a size of roughly 1 femtometer, or 1/4,000,000th of a meter. That is already a wonderfully unreasonable scale. A proton is so small that even the best ordinary images of atoms are not really photographs in the everyday sense. They are reconstructions, measurements, and indirect visualizations. The subatomic world does not politely sit still under a tiny lamp waiting to have its portrait painted, and yet a proton is still roughly 20 orders of magnitude larger than the Planck length. 20 orders of magnitude means a factor of about 100 million. In other words, the Planck length is not slightly smaller than a proton. It is not a proton's smaller cousin. It is so much smaller that the comparison becomes almost unhelpful, except as a way of showing just how quickly ordinary intuition breaks down. Imagine the difference between the size of a person and the size of the observable universe. A human body might be around 2 meters tall. The observable universe is about 93 billion light years across. That is difference so vast that it already feels more like poetry than measurement. Yet comparisons of this kind are often needed just to hint at the gap between known particle scales and the Planck length. Even then, the analogy is fragile. The Planck length is not merely another stop on the journey downward, waiting patiently below protons, quarks, and whatever else might exist. It is not like finding a smaller grain of sand after a larger grain of sand. It marks a scale where the meaning of measurement itself begins to change. Present particle accelerators do not come close to probing it directly. The Large Hadron Collider at the European Organization for Nuclear Research, known as CERN, is the most powerful particle collider ever built. It accelerates protons around a circular tunnel about 27 kilometers in circumference and collides them at extremely high energies. Those collisions allow physicists to explore tiny distances and test the standard model of particle physics. They helped confirm the Higgs boson in 2012, a major triumph for modern physics. But even the Large Hadron Collider is nowhere near the Planck length. It reaches distances far smaller than atoms, and even far smaller than protons in terms of the energy scales involved. But the Planck scale remains vastly beyond it. To probe shorter distances, physics generally needs higher energies. The effective wavelength of a particle becomes shorter as its momentum increases, which is why high-energy collisions can reveal smaller structures. The trouble is that the energy required to reach the Planck length is extraordinary. The associated Planck energy is around 1.2 times 10 to the 19 billion electron volts. That is enormously larger than the energies reached by present colliders. It is not just a matter of building the next machine slightly bigger, adding a few more magnets, and hoping the electricity bill does not look too upset. The gap is immense. In everyday terms, the Planck energy is not large like the energy of a speeding train. It is large because it is concentrated into the scale of a single particle interaction. That concentration is the key. Gravity responds to energy. At ordinary particle energies, gravity is so weak that it can usually be ignored. But at the Planck scale, the energy needed to examine such tiny distances may curve spacetime so strongly that the act of probing the distance changes the situation completely. This is why the Planck length is not just an impressive number. It is a warning label attached to our current theories. It tells us that when we combine quantum mechanics, the speed of light, and gravity, a special length naturally appears. Below that scale, the familiar language of particles moving through smooth space-time may no longer be reliable. The Planck length is therefore not simply the smallest mark on a cosmic ruler. It is not a tiny notch that future microscopes will definitely zoom in on and photograph, perhaps with a tasteful label beneath it. It is a scale at which our best descriptions of nature begin to overlap in a way we do not yet fully understand. At larger distances, physics speaks with astonishing confidence. Quantum mechanics describes atoms and particles. General relativity describes gravity, black holes, and the expanding universe. But at around 1.6 times 10 to the minus 35 meters, those two great languages must somehow be spoken together. And for now, that is where the quiet mystery remains. The Planck length is small beyond sensible comparison, but its real importance is not its smallness alone. It is the suggestion that beneath a certain scale, reality may not be waiting with smaller and smaller pieces, but with a different kind of answer altogether. The Planck length cannot really be understood as a question about space alone. That is because, in modern physics, space is not quite the separate silent stage it once appeared to be. It is woven together with time into a single structure called spacetime. And once that idea enters the picture, the smallest possible length begins to lead naturally toward the smallest meaningful interval of time as well. This was not obvious in classical physics. In Isaac Newton's view, space and time had their own independent existence. Space was the great container in which events happened, and time was the universal clock that ticked steadily for everyone. A person standing still, a person moving quickly, and a planet orbiting the sun could all be imagined as sharing the same universal now. Then Albert Einstein changed the story. In 1905, Einstein introduced special relativity. At its heart was a strange and powerful fact. The speed of light in a vacuum is the same for all observers moving at constant speeds, no matter how those observers are moving relative to one another. This was not just a small adjustment to older physics. It changed the meaning of distance, duration, and simultaneity. Simultaneity means whether two events happen at the same time. In ordinary life, this sounds simple. Two lamps turn on together, two doors close at once. Two people decide at exactly the same moment that they have forgotten why they walked into the kitchen. But special relativity shows that at the same time is not absolute. Two events that appear simultaneous to one observer may not appear simultaneous to another observer moving differently. This happens because measurements of space and time are linked through the speed of light. If everyone must measure light moving at the same speed, then space and time themselves have to adjust. A moving clock can tick more slowly relative to another observer. A moving length can appear contracted along the direction of motion. These effects are not illusions caused by bad instruments. They are part of how physical reality is structured. At everyday speeds, the effects are so tiny that we do not notice them. A bicycle ride does not noticeably rearrange time, though it may rearrange your legs the next morning. But when speeds approach the speed of light, relativity becomes impossible to ignore. Space and time are no longer separate ideas that can be measured independently in the old Newtonian way. Hermann Minkowski gave this new picture its elegant mathematical form. In 1908, he described space and time as parts of a single four-dimensional structure, space-time. An event is not described only by where it happens, it is also described by when it happens. A flash of light, a collision between particles, a star exploding, or a cup gently meeting a saucer all have both location and time. They are events in space-time. Different observers may disagree about the distance between events or the time between events, but they agree on something deeper, called the space-time interval. The space-time interval combines spatial separation and time separation into a single invariant relationship. Invariant means that it remains the same even when different observers describe space and time differently. This is one of the quiet beauties of relativity. What seems flexible on the surface hides something stable underneath. Distance and duration may shift depending on motion, but space-time has its own deeper structure. The universe is not simply a stage with a clock in the corner. It is a connected geometry of events, paths, light cones and intervals. Einstein then went further. In 1915, he introduced general relativity, his theory of gravity. In this theory, gravity is not a force in quite the Newtonian sense. It is not simply an invisible pull reaching across empty space. Instead, gravity is the curvature of space-time caused by mass and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. A planet orbiting the sun is not being pulled in exactly the same way a rope pulls a bucket. It is following the straightest possible path through curved space-time. The path looks curved to us because the geometry itself is curved. This idea has been tested with extraordinary success. General relativity explains the unusual orbit of Mercury, the bending of starlight by the sun, gravitational time dilation, black holes, the expansion of the universe, and gravitational waves. It is one of the most powerful theories ever created. But it also deepens the problem of the Planck length. If gravity is the curvature of space-time, then a theory of quantum gravity cannot merely describe particles moving through a fixed background. It may have to describe space-time itself in quantum terms. The stage may not remain classical while everything on it becomes quantum. At the deepest scale, the stage may have to join the performance. This is where the Planck length becomes more than a tiny distance. It is a signal that space-time geometry may not remain smooth forever. General relativity treats space-time as continuous and curved. Quantum mechanics introduces uncertainty, discrete energy exchanges, and wave-like behavior. Near the Planck scale, these two descriptions are forced together, and once space and time are joined, a smallest length naturally points toward a smallest time scale. The Planck time is the time it takes light to travel one Planck length in a vacuum. It is roughly 5.4 times 10 to the minus 44 seconds. That is not a tiny tick on an ordinary clock. It is a scale so brief that our usual theories cannot confidently describe what happens beneath it. So the question is not simply whether space has the smallest possible length. It is whether space-time has the smallest meaningful structure. At ordinary scales, space can seem like a calm arena, and time like a steady flow. But relativity teaches that they are one fabric, one geometry, one connected physical reality. The Planck length belongs to that fabric. It is not just a dot on a ruler. It is tied to the speed of light, to the shape of space-time, to the curvature we call gravity, and to the possibility that even geometry may have quantum limits. If reality has a smallest meaningful distance, then it may also have a smallest meaningful duration. And somewhere near that boundary, the familiar separation between where and when begins to fade into something much deeper. Very small distances cannot be treated like tiny classical boxes. That is one of the first lessons quantum mechanics teaches, and it is also one of the reasons the Planck length is so difficult to understand. In classical physics, an object can be imagined as having a definite position, a definite speed, and a definite path through space. It may be hard to measure these perfectly, but the values are assumed to exist clearly in the background. Quantum mechanics changes that picture. At the scale of atoms and particles, nature does not behave like a collection of tiny billiard balls rolling through miniature rooms. Electrons, photons, atoms, and other quantum systems are described by wave functions. A wave function is not a physical wave in the same simple sense as a ripple on a pond. It is a mathematical description containing information about the possible outcomes of measurements. Erwin Schrödinger introduced his wave equation in the 1920s, giving quantum theory one of its most famous forms. His equation describes how a wave function changes with time. It allowed physicists to calculate the behavior of electrons in atoms, the structure of energy levels, and many of the strange patterns that classical physics could not explain. But what did the wave function actually mean? Max Born gave one of the key answers. He proposed that the wave function is connected to probability. More precisely, it gives probability amplitudes, and from those amplitudes physicists can calculate the likelihood of different measurement outcomes. This was a profound shift. Quantum theory was not merely saying that particles were difficult to track, it was saying that probability itself belongs at the foundation of the theory. A quantum particle is not usually described as having one sharply defined location before it is measured. Instead, its wave function can be spread out over many possible locations. When a measurement is made, one definite result is found, but quantum mechanics only predicts the probabilities of those results. This is not how ordinary objects seem to behave. A sleeping cat is usually in one place, unless it is a particularly talented cat, and has somehow occupied every warm surface in the house. Niels Bohr became one of the central figures associated with the Copenhagen interpretation of quantum mechanics. In this broad view, the act of measurement plays a special role in connecting the mathematical possibilities of the quantum state with the definite outcomes we observe. Bohr emphasized that quantum phenomena cannot always be described using the same intuitive categories we use for ordinary objects. The experimental arrangement matters. How we ask the question affects what kind of answer nature can give. Werner Heisenberg added another essential piece, the uncertainty principle. This principle says there are limits to how precisely certain pairs of physical quantities can be known at the same time. The most famous pair is position and momentum. Position tells us where, something is. Momentum is related to how much motion it has depending on its mass and velocity. The uncertainty relation can be spoken as the uncertainty in position multiplied by the uncertainty in momentum cannot be smaller than roughly the reduced Planck constant divided by 2. This is not simply a complaint about poor instruments. It is not saying that if only we built a better microscope or polished the lenses very nicely, uncertainty would disappear. The uncertainty principle is a structural feature of quantum systems. A particle with a very sharply defined position must have a less sharply defined momentum. A particle with a very sharply defined momentum must have a more spread out position. This matters deeply when we talk about extremely small distances. To locate something inside a smaller and smaller region, its position uncertainty must become smaller. But as the uncertainty in position shrinks, the uncertainty in momentum grows. In quantum physics, forcing a system into a tiny region is not a gentle act. It brings with it larger momentum uncertainty, and larger momentum is tied to greater energy. This is why the idea of probing smaller distances does not remain simple forever. In classical thinking, you might imagine using a smaller ruler, then a smaller ruler again, and continuing downward as far as patience allows. But quantum mechanics says the world does not permit such clean separation between the object, the measuring device, and the conditions of the measurement. The more tightly you try to localize a particle, the more energy becomes involved. At atomic scales, this already shapes the structure of matter. Electrons do not simply fall into atomic nuclei because quantum rules give them stable allowed states. Particles in confined spaces have wave-like patterns and minimum energies. The smallness of the space affects the possible behavior inside it. Near the Planck length, this logic becomes even more dramatic. If localizing something into an extremely tiny region requires extremely high energy, then gravity can no longer be ignored. Energy contributes to gravity. Enough energy squeezed into a small enough region can curve space-time strongly. At some point, the attempt to measure a smaller distance may no longer reveal a smaller piece of space. It may create the conditions where space-time itself becomes part of the quantum problem. Quantum mechanics, then, is not just an extra detail added to small things, it is the rulebook of small things. It tells us that particles are described by wave functions, that outcomes are probabilistic, that measurement matters, and that certain kinds of precision are limited by nature itself. The Planck length sits at the place where these quantum rules must meet gravity and space-time. It asks what happens when uncertainty, energy, and geometry can no longer be separated. And that is why very small distances cannot be imagined as tiny classical boxes waiting quietly to be opened. At the deeper scales, the box, the key, and the space around them may all belong to the same strange quantum story. To understand why the Planck length may represent a limit to measurement, it helps to imagine a very simple experiment. Suppose you want to measure an extremely tiny distance, not just a small distance like the width of an atom, or even the width of a proton, but a distance so small that it approaches the deepest scale our current theories can name. In ordinary life, measuring something smaller usually means using a finer tool. A ruler gives way to a caliper gives way to a microscope. A light microscope gives way to an electron microscope. In particle physics, microscopes give way to high-energy collisions, where particles are used as probes of very small structure. The rule is broadly this: to examine a smaller distance, you need a probe with a shorter wavelength, and shorter wavelength means higher momentum and higher energy. This is not merely a technological inconvenience. It is built into the way quantum physics connects waves, particles, and measurement. The sharper the detail you want to see, the more energetic your probe must become. At first, this seems like a challenge of engineering. Build a bigger machine, use stronger magnets, push particles to higher speeds, make the detector more sensitive. Try not to let the budget committee see the electricity bill too early, and up to a point, this works. This is exactly the logic behind particle accelerators, including the Large Hadron Collider at the European Organisation for Nuclear Research, known as CERN. But as we imagine pushing toward the Planck length, a deeper difficulty appears. Energy is not weightless in the gravitational sense. Energy affects gravity. In general relativity, gravity responds not just to ordinary mass, but to mass and energy together. Albert Einstein's famous relation states this in spoken form as energy equals mass, multiplied by the speed of light squared. This means energy and mass are connected. A concentration of energy can have gravitational effects. Light has no rest mass, yet it still follows the curvature of spacetime. Radiation contributes to the energy content of the universe. A very energetic particle is not just a sharper probe. It is also a stronger source of gravitational influence. Now imagine trying to measure a distance smaller and smaller by concentrating more and more energy into a tinier region. Quantum mechanics says this helps reduce the wavelength of the probe, but general relativity says that concentrated energy curves space-time. At ordinary laboratory energies, that curvature is absurdly small. Gravity at particle scales is usually so weak that it might as well be whispering from another room. Near the Planck scale, however, the whisper becomes impossible to ignore. This brings us to black holes. A black hole forms when mass or energy is compressed into a region so small that an event horizon appears around it. The event horizon is not a solid surface. It is a boundary in space-time. Once something crosses it inward, it cannot escape back out to the outside universe, not even light. The size associated with a simple, non-rotating, uncharged black hole is called the Schwarzschild radius. It comes from Karl Schwarzschild's solution to Einstein's field equations in 1916, only a short time after Einstein completed general relativity. The Schwarzschild radius tells us how small a given amount of mass would need to be compressed for its escape velocity to exceed the speed of light. For a large mass, the Schwarzschild radius can be enormous. For Earth, it would be less than a centimetre. For the Sun, it would be a few kilometres. For a tiny amount of energy, it is incredibly small. But the principle remains the same. Squeeze enough energy into a small enough space, and the region becomes hidden behind an event horizon. This creates the black hole measurement problem. To see a smaller distance, you need higher energy. But if you concentrate too much energy into too small a region, the probe itself may form a black hole. Instead of revealing finer details of space, the experiment would hide them. The region you were trying to inspect would be enclosed behind a horizon, cutting off the very information you hope to obtain. This is one of the key thought experiments behind the Planck length. At scales much larger than the Planck length, quantum mechanics and gravity can often be handled separately. The quantum part tells you how short a wavelength you need. The gravitational part is usually too weak to matter. But as the distance approaches the Planck length, the two demands collide. The energy needed to localize something within that region becomes so great that its gravitational radius becomes comparable to the region itself. That is the heart of the limit. Below roughly the Planck length, an attempt to measure a smaller distance may not produce a clearer picture. It may produce gravitational collapse, or at least a situation where our current theories can no longer describe the measurement in an ordinary way. The harder you try to focus on the tiniest possible point, the more space-time pushes back. This does not prove that space is made of indivisible grains. It does not show us a final pixel under a cosmic microscope. What it shows is subtler. The idea of measuring a distance depends on the physical tools available, and those tools obey both quantum mechanics and general relativity. When the required energy becomes extreme enough, measurement itself changes character. The Planck length therefore marks a boundary where the question, what is happening at an even smaller distance, may no longer work in the familiar sense. It is not that nature is simply hiding a smaller object and refusing to share. It is that the act of looking more closely may create a horizon between the question and the answer. At ordinary scales, a ruler can sit quietly beside what it measures. At quantum scales, the ruler becomes part of the interaction. Near the Planck scale, the ruler may become heavy enough in the gravitational sense to disturb space-time itself. And that is why measuring too closely becomes one of the strangest problems in physics. The smallest length may not be protected by a wall made of matter, but by the combined logic of quantum uncertainty, energy, gravity, and black holes. The universe does not merely get smaller, it begins to defend the meaning of distance itself. If the Planck length is the smallest length we can sensibly name, then the Planck time is its partner in time. It is the smallest tick that naturally appears when the speed of light, quantum mechanics, and gravity are brought together. Not a tick on a real clock, and not a tiny frame in a cosmic film strip, but a scale where our ordinary idea of time begins to lose its familiar shape. The Planck time is defined as the time light would take to travel one Planck length in a vacuum. Since the Planck length is roughly 1.6 times 10 to the minus 35 meters, and light travels at about 300 million meters per second, that time is almost impossibly brief. The Planck time is roughly 5.4 times 10 to the minus 44 seconds. That is a decimal point followed by 43 zeros before the first meaningful digits. It is so short that even the fastest processors measured in particle physics seem leisurely beside it. A second, by comparison, is an enormous stretch of time. If ordinary time were a vast ocean, the Planck time would not be a ripple on its surface. It would be something far beneath the idea of a ripple, down where the word moment starts to feel too large. But again, care is needed. The Planck time is not known to be a literal smallest slice of time. It does not mean the universe definitely updates itself every Planck time, like a computer ticking through frames. That image is tempting, but it is not established physics. The Planck time is better understood as a natural scale, produced by the same three constants that produce the Planck length: the speed of light, Newton's gravitational constant, and the reduced Planck constant. The speed of light is especially important here, because it ties length and time together. In relativity, space and time are not separate background ingredients. They form space-time. A distance can be connected to a time by asking how long light takes to cross it. So if there is a natural smaller scale of length in our current theories, there is also a natural smaller scale of time. This is why the Planck length and Planck time belong together. A tiny length is not just a tiny piece of space, it is part of space-time. To speak about distances that's small is also to speak about durations that's short. The more deeply physics examines space, the more it is forced to examine time as well. The Planck time becomes especially important when physicists think about the earliest universe. In standard Big Bang cosmology, the universe is not imagined as an explosion into empty space, but as the expansion of space itself from a much hotter, denser state. The Belgian physicist Georges Lemaitre was one of the first to propose that the universe was expanding from an earlier dense state. Edwin Hubble's observations of galaxies helped establish that distant galaxies are generally receding from us, which became central evidence for cosmic expansion. When the equations of general relativity are run backward, the universe becomes hotter, denser, and smaller. At very early times, matter and radiation were compressed into extreme conditions. But if we keep pushing backward toward the beginning, the equations eventually lead into a region where known physics can no longer be trusted on its own. This region is often called the Planck era. It refers to the earliest interval in standard cosmological thinking, before roughly one Planck time after the beginning. But this does not mean scientists have directly observed this era. They have not. It is not a photographable moment. It is not preserved like an old frame from the universe's baby album, which is probably for the best, because baby universes may not enjoy being photographed. The Planck era is a boundary of knowledge. It is where general relativity and quantum theory would both be needed at full strength. General relativity describes space-time and gravity. Quantum theory describes matter, energy, fields, and uncertainty. In the Planck era, the universe would have been so dense and energetic that space-time itself may have required a quantum description. After that earliest unknown region, physics becomes more confident. The universe expanded and cooled. Much later, atomic nuclei formed. Later still, electrons joined with nuclei to form neutral atoms in a period called recombination. At that point, light could travel freely through space. That ancient light is now observed as the cosmic microwave background. The cosmic microwave background is one of the strongest pieces of evidence for the hot early universe. It was discovered in the 1960s by Arno Penzias and Robert Wilson, and later measured in increasing detail by missions such as COBE, WMAP, and the European Space Agency's Planck satellite. These observations do not show the Planck era itself. They show the universe hundreds of thousands of years later. Still, they help confirm that the universe really did pass through a hot, dense early state. So the Planck time sits beyond direct observation, at the edge of extrapolation. It marks the point where saying earlier becomes difficult, not because time necessarily began there in a simple way, but because our current equations no longer give a complete answer. Some theories suggest a beginning, others suggest a bounce, others suggest that time itself may emerge from something deeper. At the Planck time, the word before may not behave the way it does in everyday life. This is the quiet lesson of the Planck time. The smallest length question is also a smallest time question. Once space and time are joined into space-time, we cannot ask how small space can be, without also asking how finely time can be divided. The two ideas meet at the same boundary. The Planck time is not a proven final tick of reality. It is a sign that the clocks of ordinary physics cannot simply be wound backward forever without meeting a deeper problem. It tells us that near the beginning of the universe, and near the smallest scales of space-time, time itself may require a new theory. And that is why this tiny duration matters. It is not just short. It is the point where relativity, quantum mechanics, and gravity all begin speaking at once, and where our familiar sense of time becomes part of the mystery rather than merely the clock measuring it. Quantum gravity is the name given to one of the deepest unfinished tasks in physics, describing gravity according to quantum principles. It is not a single completed theory, but a problem, a search, and a family of possible routes toward a more complete picture of reality. The reason this is so difficult is not that gravity has failed. Quite the opposite. Gravity has succeeded almost too well. Albert Einstein's general relativity describes gravity as the curvature of space-time caused by mass and energy. It explains planetary orbits, gravitational time dilation, the bending of light, black holes, the expansion of the universe, and gravitational waves. On large scales, it is one of the most accurate and beautiful theories human beings have ever produced. Quantum theory has also succeeded with astonishing precision. In its modern form, quantum field theory describes particles as excitations of underlying fields. The standard model of particle physics uses quantum field theory to describe the electromagnetic interaction, the weak interaction, and the strong interaction. These are three of the four known fundamental interactions. The standard model explains electrons, quarks, neutrinos, photons, gluons, the Higgs boson, and many of the processes that shape matter at the smallest tested scales. But gravity is not included in the standard model in the same way. It remains outside the quantum field theory framework that describes the other fundamental forces. And this is where the unease begins. General relativity and quantum field theory are both extraordinarily successful, but they are built on different assumptions about space-time. In general relativity, space-time is dynamic. It bends, stretches, curves, evolves, and responds to mass and energy. It is not merely the place where physics happens, it is part of the physics. In ordinary quantum field theory, however, fields are usually described as existing on a background space-time. That background may be flat, as in special relativity, or curved in more advanced versions of the theory, but it is often treated as something already there. The quantum fields do their strange and delicate work on a stage that is not itself fully quantum. This difference matters most when gravity becomes strong and distances become tiny. If spacetime is the gravitational field, and if all other fields are quantum, then it becomes natural to ask whether spacetime itself must also be quantum. A true theory of quantum gravity would not merely place particles inside spacetime. It would explain what spacetime is when quantum uncertainty can no longer be ignored. At ordinary scales, this problem can be politely avoided. The gravity between two electrons is so weak that it is almost always irrelevant. Electromagnetism overwhelms it completely. The gravitational attraction between tiny particles is so faint that, in particle physics experiments, gravity usually has no practical role at all. It is there, technically, like someone whispering from a different building. This is why institutions such as the European Organisation for Nuclear Research, known as CERN, can test the standard model so successfully without needing a full theory of quantum gravity. The Large Hadron Collider explores incredibly small distances and high energies by human standards, but still far below the energy where gravity is expected to become strong in particle interactions. On the other hand, general relativity is tested beautifully in places where gravity is strong or spacetime curvature is important. The Laser Interferometer, Gravitational Wave Observatory, known as LIGO, has detected gravitational waves from merging black holes and neutron stars. These ripples in spacetime match Einstein's predictions with remarkable accuracy. The Event Horizon Telescope collaboration has produced images of the shadow regions around supermassive black holes, giving another extraordinary test of gravity in extreme environments. So the strange situation is this. Quantum theory works brilliantly where things are small, and general relativity works brilliantly where gravity is strong. But where things are both extremely small and gravitationally extreme, we do not yet have a complete theory. This is the territory of quantum gravity. The Planck length matters because it marks the scale where this missing theory is expected to become unavoidable. It is built from the reduced Planck constant, Newton's gravitational constant, and the speed of light. These constants bring together quantum mechanics, gravity, and relativity. Their combination tells us that at around 1.6 times 10 to the minus 35 meters, our separate theories can no longer be trusted to remain separate. The difficulty is that this scale is far beyond direct experimental reach. To probe the Planck length directly would require energies vastly greater than those available in any present particle accelerator. The associated Planck energy is so enormous for a single particle interaction, the direct tests are not merely difficult but unimaginably far from current technology. There is also a mathematical difficulty. When physicists try to quantize gravity in the most straightforward way, treating it like another quantum field, the calculations produce infinities that cannot be handled as neatly as in the standard model. Quantum electrodynamics, the quantum theory of the electromagnetic interaction, can make predictions of extraordinary accuracy because its infinities can be controlled through renormalization. Gravity resists this simple treatment. That does not mean quantum gravity is impossible. It means gravity may require a deeper kind of theory. Perhaps spacetime is made of quantum loops. Perhaps particles are not points but tiny strings. Perhaps spacetime emerges from quantum information. Perhaps the correct answer is stranger than all of these, which would be very on brand for the universe. What matters is the shared lesson. The Planck length is not just small, it is the scale at which our two greatest descriptions of reality meet without yet fully agreeing. General relativity says space-time is geometry. Quantum theory says the small world is governed by uncertainty, probability, and quantist fields. Quantum gravity asks what happens when geometry itself must obey quantum rules. Until that question is answered, the Planck length remains a boundary marker. It tells us where the smooth space-time of general relativity may stop being enough. It tells us where quantum field theory may need a deeper foundation, and it reminds us that the smallest length reality allows is not only a question about size, but a question about what space and time truly are. At ordinary scales, space-time appears calm. It curves around stars and planets. It carries light across the universe. It stretches with cosmic expansion and ripples gently when black holes collide. General relativity describes this space-time as smooth geometry, like an invisible fabric whose shape tells matter how to move. But near the Planck length, some physicists have wondered whether that smoothness can survive. John Archibald Wheeler gave one of the most memorable images for this possibility. He suggested that at extremely tiny scales, space-time might become restless and irregular, no longer resembling a smooth geometric surface. He called this idea space-time foam. The phrase is not meant to imply that space is literally made of bubbles like soap in a bath. It is a conceptual image, a way of imagining what might happen if quantum uncertainty applies not only to particles and fields, but to geometry itself. At large scales, space-time could look smooth and continuous, but at the Planck scale, it might fluctuate violently, with tiny distortions in distance, duration, and shape appearing and disappearing. The idea comes partly from the behaviour of quantum fields. In quantum theory, even empty space is not truly empty in the classical sense. A vacuum is not a perfectly dead nothingness. Quantum fields still have fluctuations. They cannot simply sit at exactly zero with perfect calm, because quantum mechanics does not allow that kind of absolute stillness. These vacuum fluctuations are not just a poetic idea. They have measurable consequences in certain situations. One famous example is the Casimir effect, predicted by Hendrik Casimir in 1948. When two uncharged conducting plates are placed extremely close together in a vacuum, quantum field theory predicts a tiny attractive force between them. This effect has been measured, and it shows that the quantum vacuum has physical structure. But it is important to be careful. The Casimir effect is evidence for quantum vacuum effects in fields. It is not direct evidence that space-time itself becomes foam. It does not show little bubbles of geometry under a microscope. It simply helps us understand why physicists take quantum fluctuations seriously. If fields fluctuate even in vacuum, then perhaps a true quantum theory of gravity would allow space-time geometry to fluctuate too. Wheeler was one of the great figures of 20th century gravitational physics. He worked on nuclear physics, black holes, wormholes, and the foundations of general relativity. He helped popularize the term black hole, and he used the word geometrodynamics to describe the idea that physics could be understood through the dynamics of geometry. For Wheeler, space-time was not a passive background. It was active, flexible, and perhaps, at the deepest level, uncertain. In general relativity, geometry is gravity. Curvature is not just drawn on top of space, it is part of what space-time is. So if gravity must be quantum, then geometry may not remain fixed and perfectly smooth. A quantum space-time might have uncertainty in its shape, just as a quantum particle can have uncertainty in its positional momentum. This is where space-time foam becomes useful as an image. Imagine looking at the ocean from high above. From far away, the surface may look smooth and calm. From closer in, waves appear. Closer still, there are ripples, bubbles, spray, and turbulence. The smooth surface was not false exactly. It was a large-scale description. It worked, because the smaller disturbances were invisible from that distance. Space-time may be similar, although this is only an analogy. On human scales, planetary scales, and even astronomical scales, space-time can be described as smooth with astonishing success. But near the Planck length, the idea of a precise distance between 2 points may become unstable. Tiny fluctuations in geometry could mean that distance itself is no longer sharply defined in the familiar way. This would affect more than distance. It could also affect duration, because space and time are joined as spacetime. If geometry fluctuates, then the time interval between events might also become uncertain at the smallest scales. Even causality, the ordering of cause and effect, could become more subtle if spacetime structure is not perfectly fixed. That last idea must be handled gently. There is no experimental proof that causality breaks down at the Planck scale. Physics is not telling us that yesterday might casually wander after tomorrow because spacetime forgot its diary. Rather, the point is that our classical idea of a definite, smooth spacetime may not be the final language. Near the Planck length, quantum gravity may require a more careful description of what it means for events to be separated, connected, or ordered. Spacetime foam is therefore not a confirmed picture of reality. It is not part of the standard model. It has not been directly observed by CERN, LIGO, the Event Horizon Telescope, or any other experiment. It is a speculative but influential concept, a way of thinking about why classical geometry may fail when pushed to the smallest possible scales. And that is precisely why it belongs in the story of the Planck length. The Planck length may not be a final dot at the bottom of space. It may not be a tiny bead from which the universe is assembled. Instead, it may mark the place where the smooth idea of geometry stops being trustworthy. Above that scale, spacetime can behave like a calm stage. Below it, or near it, the stage may no longer stay still. It may fluctuate, blur, fold, or require a description that does not resemble ordinary geometry at all. The smallest length reality allows, then, might be less like a final tile and more like the shoreline of classical meaning. From far away the beach looks smooth. Up close it becomes grains, foam, water, and motion. And at the Planck scale, space-time itself may be the thing that begins to shimmer. One possible answer to the mystery of the Planck length is that space itself may come in quantum units, not in the simple sense of tiny square pixels, and not as a neat cosmic chessboard hidden beneath reality, but in a subtler mathematical sense. This is the direction explored by loop quantum gravity. Loop quantum gravity is one of the major attempts to build a theory of quantum gravity. It begins with a bold idea. If gravity is the geometry of space-time, as general relativity says, and if the world is quantum at its deepest known levels, then perhaps geometry itself must be quantum too. Space may not be a fixed background on which quantum fields move. Space may itself be made of quantum states. This is a very different way of thinking. In many versions of quantum field theory, fields exist on a background space-time. The electromagnetic field, the electron field, the quark fields, and other fields are described as living in space-time. The stage is already there. The actors behave quantum mechanically on top of it. Loop quantum gravity tries to remove that fixed stage. It asks what happens if space-time geometry itself is part of the quantum system. In this view, quantum gravity is not just a theory of particles moving through space. It is a theory of the quantum structure of space. Important figures in the development of loop quantum gravity include Abhay Ashtekar, Carlo Rovelli, Lee Smolin, and Thomas Thiemann. Ashtekar introduced new mathematical variables that helped reformulate general relativity in a way better suited to quantization. Rovelli and Smolin helped develop the loop representation and the physical interpretation of the theory. Thiemann made major contributions to the mathematical structure of the dynamics. Together with many others, they helped shape loop quantum gravity into a serious research program. The central idea is that geometry can have quantum states. Just as an atom can only have certain allowed energy levels, space in loop quantum gravity can have certain allowed geometric properties. In particular, areas and volumes can have discrete spectra. A discrete spectrum means that the possible values are not continuous, but come in separated steps. This does not mean every length is simply a multiple of the Planck length in a straightforward way. It also does not mean space is built from tiny cubes. That image is easy to picture, but it is misleading. Loop quantum gravity does not describe space as a little square grid. like a video game map waiting for someone to render the trees. The structure is more relational and abstract. One of the key mathematical tools is the spin network. A spin network is a graph made of links and nodes, labelled with quantum information. These labels are connected to geometric quantities such as area and volume. The links can be thought of as carrying information about areas, while the nodes relate to volumes, but they should not be imagined too literally as wires and beads floating inside ordinary space, because ordinary space is the thing being described. That last point is important. A spin network is not placed inside space in the usual way. It is a description of quantum space itself. The relationships between the parts of the network help define the geometry. In a sense, space is not the container of the network. The network is part of what gives space its geometric meaning. This is difficult because our imagination is trained by everyday objects. We want to ask where the spin network is located. But if it is describing space itself, that question becomes slippery. It is a little like asking where the map of all locations is located before there is any location for it to sit in. The mind does not love this sort of thing. It prefers tables, chairs, and perhaps a biscuit. The discreteness predicted in loop quantum gravity is one reason the theory is often connected to the Planck length. The smallest non-zero areas and volumes in the theory are associated with the Planck scale. This suggests that the smooth geometry of classical general relativity may be an approximation, emerging only when many quantum units of geometry are viewed together at larger scales. An analogy is the surface of a lake. From far away it looks smooth. Up close it is made of molecules, moving and interacting. The smooth surface is real as a large-scale description, but it is not the deepest level. In loop quantum gravity, smooth spacetime may be something similar, a large-scale approximation to a deeper quantum geometry. But again, the analogy must not be pushed too far. Molecules exist in space. Quantum geometry in loop quantum gravity is supposed to describe space. So the deeper structure is not made of tiny material grains sitting inside a pre-existing arena. It is more like a network of relations from which the familiar arena can emerge. This has implications for singularities. In classical general relativity, the equations can lead to singularities, such as the center of a black hole or the earliest moment of the Big Bang. A singularity is where quantities like density or curvature become infinite, and the theory stops giving a physically meaningful answer. Most physicists do not treat singularities as real little points of infinite density. They treat them as signs that the theory has reached its limit. Loop quantum gravity offers possible ways to avoid such infinities. If geometry is quantized, then space-time may not be able to shrink smoothly to zero size in the classical way. There may be a smallest meaningful area or volume, preventing the formation of an actual infinite singularity. This idea appears in loop quantum cosmology, a related application of loop quantum gravity to the universe as a whole. In some loop quantum cosmology models, the Big Bang singularity is replaced by a quantum bounce. Instead of the universe beginning from an infinitely dense point, a previous contracting phase reaches an extremely dense quantum gravitational state, then rebounds into expansion. This is a fascinating possibility. It suggests that the Big Bang may not be the absolute beginning of everything, but a transition from an earlier state. However, it is important to remain careful. Loop quantum cosmology is not confirmed by observation. It is a model inspired by loop quantum gravity, and its conclusions depend on assumptions and simplifications used to make the mathematics manageable. Loop quantum gravity also faces major open questions. Physicists still work on deriving ordinary smooth spacetime from the theory in a complete and convincing way. They also study how matter fields fit into the framework, how black holes should be described, and whether the theory produces predictions that can be tested experimentally. A theory of quantum gravity cannot simply be beautiful. It must eventually connect with nature. At present, There is no direct experimental evidence that loop quantum gravity is the correct description of spacetime. No detector has measured a spin network. No telescope has confirmed that area and volume are quantized in the specific way the theory suggests. The Planck scale is so far beyond direct access that all approaches to quantum gravity face a serious testing problem. Still, loop quantum gravity matters because it takes the Planck length seriously as a clue. It asks what physics looks like if geometry is not infinitely divisible, if smooth spacetime is not fundamental, and if area and volume have quantum structure. It does not merely add quantum particles to gravity. It tries to quantize the very fabric that gravity describes. This makes the theory one of the clearest examples of how the smallest length might change the meaning of space. If loop quantum gravity is right, then the Planck scale is not just a warning that our measurements fail. It may be where the smooth world gives way to quantum geometry, and yet the answer remains open. Space may be discrete in this subtle relational way, or it may be continuous but limited by measurement, or it may emerge from something still deeper, where even the words continuous and discrete are no longer quite the right tools. Loop quantum gravity does not close the mystery. It gives the mystery a possible shape. It suggests that beneath the calm geometry of everyday reality, space itself may have quantum structure, not as a simple grid, but as a web of relationships whose large-scale appearance becomes the smooth space-time we know. The smallest length reality allows, in this view, is not the edge of a tiny box. It is the first hint that geometry may have a quantum language of its own. String theory offers another possible route toward the smallest scales of reality. Like loop quantum gravity, it is an attempt to bring quantum mechanics and gravity into the same framework. But it begins from a very different idea. Instead of asking whether space itself is made from quantum geometry, string theory asks what happens if the smallest things in nature are not point-like at all. In ordinary particle physics, fundamental particles are usually treated as point-like excitations of fields. An electron, for example, is not imagined as a tiny ball with a little surface and a miniature personality. In quantum field theory, it is an excitation of the electron field. Quarks, photons, gluons, and other particles are also described through fields, and in the standard model they behave, as far as experiments have shown, like point-like entities with no internal size. This point-like picture works extremely well. It has allowed physicists to make predictions of astonishing precision. But it also creates difficulties when gravity is brought into quantum theory. Exact mathematical points can lead to troublesome infinities. If interactions are squeezed into zero size, calculations may become uncontrollable. The smaller the region, the more violently the mathematics can misbehave, like a calm cat suddenly introduced to a bathtub. String theory changes the starting point. It proposes that the fundamental objects are not zero-dimensional points, but tiny one-dimensional strings. These strings can vibrate in different ways, and different patterns of vibration appear as different particles. One vibration might correspond to an electron, another might correspond to a quark, another might correspond to a photon. Most importantly, string theory naturally contains a particle with the properties expected of the graviton, the hypothetical quantum particle associated with gravity. This is one reason string theory became such an important candidate for quantum gravity. It was not simply trying to add gravity afterward. Gravity seemed to emerge from the mathematics of the strings themselves. The early development of string theory involved several important figures, including Yoichiro Nambu, Holger Beck-Nielsen, and Leonard Susskind, who helped reinterpret early models in terms of tiny vibrating strings. Later, Michael Green and John Schwartz made major progress in superstring theory in the 1980s, showing that certain mathematical inconsistencies could cancel in particular versions of the theory. Edward Witten then played a central role in connecting different string theories through what became known as M-theory, helping reveal that they may be different limits of a deeper structure. The characteristic length scale of strings is often associated with the Planck scale, although the exact relationship depends on the particular version of the theory and on how its parameters are set. The key idea is that a string is extended. It has length. It is not an exact point. This means interactions are not concentrated into a single zero-size location in quite the same way. That extended nature can soften some of the short-distance problems that appear in point-particle theories. Instead of two particles meeting at a perfect mathematical point, strings interact by joining and splitting along tiny extended shapes. The interaction is spread out. The mathematics becomes less singular. In some sense, string theory suggests that below a certain scale, the idea of probing an exact point may not be the right way to describe nature. This connects naturally to the Planck length. If the fundamental objects are extended strings, then the smallest meaningful distances may be limited not because space is made of tiny blocks, but because the objects used to probe space cannot be compressed into exact points. The deepest level would not be a collection of point-like particles moving through a smooth background, but a world where the basic ingredients already have a smallest characteristic extent. String theory also introduces extra dimensions. This sounds dramatic, and admittedly it does have a certain science fiction sparkle. But in the theory, extra dimensions are not imagined as ordinary directions you could simply point toward if only you stretch properly after breakfast. They are mathematical and physical possibilities required by the consistency of the theory. The roots of this idea go back to Kaluza-Klein theory, developed by Theodor Kaluza and Oscar Klein in the early 20th century. They explored the possibility that adding an extra spatial dimension could help unify gravity and electromagnetism. In modern string theory, extra dimensions are often compactified, meaning they are curled up or hidden at extremely small scales, so they do not appear as large everyday directions. Different ways of compactifying these extra dimensions can lead to different low-energy physics. This is one reason string theory has become both powerful and difficult. It contains a vast landscape of possible solutions, and connecting the mathematics uniquely to the universe we observe remains an enormous challenge. String theory has also influenced many areas beyond its original goal. It has shaped research into black holes, quantum information, holography, and the deep relationship between gravity and geometry. It has produced mathematical tools used across theoretical physics. Even physicists who do not think string theory is the final answer often recognize its influence. But balance is essential. There is currently no direct experimental evidence that string theory describes the fundamental structure of nature. No experiment has observed a string. No particle accelerator has reached energies where the string scale would clearly reveal itself, if that scale is near the Planck scale. The theory remains mathematically rich and scientifically serious, but not experimentally confirmed. This matters for the question of the smallest length. String theory gives a possible answer, but not a settled one. It suggests that nature may avoid the problems of infinitely small points by replacing them with extended objects. It suggests that the Planck scale may be where the point-particle picture breaks down, but it does not yet prove that this is how reality truly works. Still, the idea is beautiful in its own careful way. The smallest things may not be dots. They may be tiny vibrating structures, too small to see directly, whose patterns give rise to the particles and forces we observe. Space itself may include hidden dimensions, folded so tightly that ordinary life passes through them without noticing. If loop quantum gravity imagines space gaining a quantum geometry, string theory imagines matter and force arising from objects that are not point-like to begin with. Both approaches challenge the assumption that reality can be understood by dividing space into smaller and smaller points forever. The Planck length, in this view, is not a final mark on a ruler. It is a sign that the ruler may have been the wrong metaphor. Beneath the familiar world, the deepest objects may have extension, vibration, and hidden structure. And at the smallest scales, reality may not be made of points at all, but of something more like music written into the geometry of the universe. One of the strangest clues about the smallest scales of reality comes not from trying to look at tiny distances directly, but from asking how much information can fit inside a region of space. At first, that sounds like a very different question. Length is about size. Information is about states, possibilities, and descriptions. But in modern physics, especially, near black holes, these ideas begin to meet in surprising ways. The clue is called the holographic principle. The word holographic can be slightly misleading because it may make the universe sound like a cheap projection or a trick played by a cosmic magician with an alarming amount of spare time. But the holographic principle is not saying that reality is fake. It is saying something more careful and more interesting. In a theory that includes gravity, the amount of information contained in a region may be related not to the volume inside it, but to the area of its boundary. That is deeply strange. In ordinary life, volume seems like the natural measure of capacity. A bigger box can hold more things than a smaller box. A larger room can contain more furniture, more air, and more places to lose your keys. So we might expect the information in a region of space to grow with its volume. Black holes suggest otherwise. Jacob Bekenstein was one of the first physicists to take seriously the idea that black holes have entropy. Entropy is often described as a measure of disorder, but more precisely, it is related to the number of possible microscopic states that can produce the same large-scale appearance. A black hole looks simple from the outside. It can be described by properties such as mass, electric charge, and rotation. But if it has entropy, then it must somehow contain or represent a vast number of possible internal states. Stephen Hawking then showed that black holes are not completely black. By combining quantum field theory with curved spacetime, he found that black holes should emit radiation, now called Hawking radiation. This was astonishing because it connected gravity, quantum theory, temperature, and entropy in one physical system. Together, Bekenstein and Hawking revealed something profound. The entropy of a black hole is not proportional to the volume inside the black hole. It is proportional to the area of the event horizon. The event horizon is the boundary beyond which nothing can escape to the outside universe, not even light. In spoken form, the idea is, black hole entropy is proportional to the horizon area measured in Planck areas. A Planck area is the Planck length multiplied by the Planck length. This means the Planck scale appears directly in the counting of black hole entropy. The larger the horizon area, the more Planck-sized area units can fit on it, and the more entropy the black hole has. It is as though nature keeps track of gravitational information using the boundary, not the full interior volume. Gerard 't Hooft and Leonard Susskind developed this idea into the holographic principle. They argued that the maximum information inside a region with gravity may be encoded on the boundary of that region, with roughly one fundamental unit of information per Planck area. This does not mean there are literally glowing letters written on the edge of space. It means the deepest description of a volume may be mathematically equivalent to information living on a lower dimensional boundary. This idea became much more concrete through the work of Juan Maldacena in 1997. Maldacena proposed the anti-de Sitter conformal field theory correspondence. It is usually shortened, rather mercifully, because otherwise physicists would spend half their careers just saying its name. The correspondence describes a relationship between a gravitational theory and a kind of spacetime called anti-de Sitter space, and a quantum field theory without gravity on its boundary. In this setting, a theory with gravity in a higher dimensional space can be equivalent to a theory without gravity in one fewer dimension. It is one of the most important discoveries in modern theoretical physics. This does not mean our universe is known to be anti-de Sitter space. It is not, at least not in the simple form used in Maldacena's original correspondence. Our universe appears to have a positive cosmological constant, while anti-de Sitter space has a different large-scale structure. Still, the correspondence gives physicists a powerful example of holography actually working in a precise mathematical way. The importance for the Planck length is subtle, but enormous. Black hole entropy suggests that when gravity is involved, information is counted in units connected to Planck area. That means the Planck length is not merely a possible limit for distance measurement, It may be part of the deep accounting system of space-time itself. This changes how we think about space. If the information in a region is limited by boundary area rather than volume, then space may not be as independent and straightforward as it appears. The inside of a region may, in some deep sense, be described by relationships on its boundary. Geometry and information become intertwined. Holography also connects to the idea that space-time might be emergent. If a higher dimensional gravitational world can be equivalent to a lower dimensional quantum theory, then perhaps space-time is not fundamental in the way classical physics assumed. It may arise from quantum information, entanglement, and boundary relationships. This does not give a simple answer to the smallest length reality allows. It does not say that space is definitely made of Planck-sized squares. It does not turn every horizon into a literal screen or every star into a suspiciously well-rendered object. The lesson is more delicate. Gravity seems to limit information in a way that involves areas measured at the Planck scale. The holographic principle is therefore one of the deepest clues that the Planck length matters. It suggests that the smallest meaningful scales are tied not only to measurement, energy, and black holes, but also to information itself. At large scales, space feels like volume. It feels like rooms, distances, depths, and open directions. But near the foundations of gravity, space may also be a way of organizing information. And if that is true, the Planck length may be less like the size of a tiny object, and more like the unit by which space-time keeps its most secret records. Black holes are among the best natural laboratories for thinking about the Planck scale, even though the deepest Planck scale details are hidden from us. They are places where gravity becomes extreme, where time behaves strangely, where information seems to face a crisis, and where quantum mechanics can no longer be treated as a small optional detail. A black hole forms when enough mass or energy is compressed into a small enough region that an event horizon appears. The event horizon is not a solid surface. It is not a shell, a wall, or a dramatic glowing membrane waiting politely in space. It is a boundary in space-time. Once something crosses inward through that boundary, it cannot return to the outside universe by any ordinary path. Not even light can escape. For a large black hole, the event horizon itself may not feel locally dramatic to someone falling through it. This is one of the stranger lessons of general relativity. If the black hole is supermassive, the tidal forces at the horizon can be mild. Tidal forces are differences in gravity from one part of an object to another. They stretch and squeeze. Near a small black hole, those differences can be enormous at the horizon. Near a very large black hole, they may only become destructive much deeper inside. The truly troubling part of the classical black hole lies not at the horizon, but toward the centre. In the simplest solutions of general relativity, matter continues inward toward a singularity. A singularity is a place where classical equations predict quantities such as density and spacetime curvature becoming infinite. That sounds like a physical object, but most physicists treat it more carefully. A singularity is usually understood as a sign that general relativity has been pushed beyond its valid range. Roger Penrose played a central role in showing, through singularity theorems, that singularities are not just quirks of overly simple mathematical models. Under broad conditions, gravitational collapse in general relativity leads to incomplete paths in space-time. Stephen Hawking extended singularity work into cosmology and black hole physics, helping reveal how deeply these questions reach. Kip Thorne made major contributions to black hole theory, relativistic astrophysics, and gravitational waves, helping connect the mathematics of black holes to observable physics. These ideas make black holes central to the question of the Planck length. General relativity predicts that collapse can continue toward infinite curvature. Quantum gravity is expected to say, somehow, no. Not necessarily with a neat little signpost, and probably not in handwriting we would immediately understand, but with new physics that prevents the classical infinity from being the final story. the event horizon raises a different problem. In the 1970s, Stephen Hawking showed that black holes should not be perfectly black. When quantum field theory is considered near a black hole horizon, black holes emit radiation. This is now called Hawking radiation. The effect is incredibly weak for large astrophysical black holes, but conceptually it is enormous. It brings together quantum mechanics, gravity, thermodynamics, and curved spacetime. Hawking radiation means that a black hole can slowly lose energy. If it loses energy, it loses mass. If it loses mass, it can gradually shrink. For a black hole with the mass of a star, this process takes an unimaginably long time, far longer than the present age of the universe. But in principle, if the process continues, a black hole could eventually become extremely small, and as it becomes smaller, the physics becomes harder. The final stages of black hole evaporation would involve enormous temperatures, intense curvature, and scales approaching the Planck length. That is exactly where our current theories stop being enough. Quantum field theory on a curved background can describe the early, gentle stages of Hawking radiation, but the final stage likely requires a full theory of quantum gravity. Then there is the black hole information paradox. In quantum mechanics, information about the state of a system is not supposed to be fundamentally destroyed. It may become scrambled, hidden, or practically impossible to recover, but the underlying evolution is expected to preserve it. Hawking's original calculations seem to suggest that black hole radiation is thermal, carrying no detailed information about what fell in. If the black hole eventually evaporates completely, what happens to that information? This is not just a puzzle about bookkeeping. It reaches into the heart of reality. If information is destroyed, quantum mechanics may need revision. If information is preserved, then black hole evaporation must encode it somehow, perhaps in extremely subtle correlations within the radiation. Either way, the horizon, entropy, and quantum structure of spacetime become unavoidable. Black holes also connect to the Planck length through horizon microstructure. The entropy of a black hole is proportional to the area of its event horizon measured in Planck areas. This suggests that the horizon may have a deep quantum description, even if it looks smooth in classical general relativity. The horizon may not be just an empty boundary. It may be connected to the microscopic degrees of freedom of quantum gravity. This does not mean we can look at a real black hole and see Planck-sized details glittering on its surface. The Event Horizon Telescope has imaged the shadow regions around supermassive black holes, including the object in the galaxy Messier 87 and the black hole at the centre of the Milky Way. These are extraordinary achievements, but they do not resolve Planck-scale horizon structure. The details are far too small and far too deeply hidden. Still, black holes show us where the smallest length becomes unavoidable. They contain horizons where time and causality behave differently. They lead to singularities where classical geometry breaks down. They radiate through quantum effects. They carry entropy linked to Planck area. They threaten, or at least challenge, the quantum preservation of information. In this sense, a black hole is not merely an object in space. It is a meeting point for the deepest ideas in physics. Length, time, energy, entropy, information, gravity, and quantum mechanics all collide there. The Planck length enters not as a decorative tiny number, but as the scale where the hidden machinery is expected to live. Black holes remind us that the smallest length reality allows may not be found by simply building a better microscope. It may be revealed indirectly by understanding what happens when spacetime bends so strongly that even light cannot leave, and when quantum theory quietly insists that information still matters. At the horizon, reality whispers in geometry. Near the singularity, classical physics loses its voice. And somewhere near the Planck scale, a deeper theory is expected to explain how black holes truly keep their secrets. The smallest length reality allows is not only a question about tiny distances. Strangely, it is also a question about the largest story physics can tell, the origin of the universe. When cosmologists look backward through time, following the expansion of space in reverse, the universe becomes hotter, denser, smaller, and more extreme. Keep going far enough, and the story approaches a point where the Planck scale can no longer be avoided. Standard Big Bang cosmology is one of the great successes of modern science. It does not say that the universe exploded into empty space from a single point, like a firework going off in a pre-existing darkness. It says that space itself has been expanding from an earlier state that was much hotter and denser than the universe is today. Galaxies are now carried apart as the fabric of space expands between them. This picture explains a remarkable amount. It explains why distant galaxies are generally receding from us. It explains why the universe was once hot enough for matter and radiation to interact intensely. It explains the formation of light elements such as hydrogen, helium, and small amounts of lithium in the early universe. And it explains the existence of the cosmic microwave background, the oldest light we can observe directly. But standard Big Bang cosmology is strongest after the universe has already moved beyond its most extreme earliest moments. It is very good at describing the young hot universe once known physics can be applied with confidence. It is much less certain when we ask about the absolute beginning, if there was an absolute beginning at all. Run the equations of general relativity backward, and the universe becomes denser and hotter. Keep extrapolating, and the equations point toward conditions where density and temperature grow without limit. But infinities in physics are often warning signs. They usually mean that a theory is being pushed outside the range where it should be trusted. The Planck era is the name often given to the earliest period, before about 1 Planck time after the beginning, in the simplest backward extrapolation. The Planck time is roughly 5.4 times 10 to the minus 44 seconds. During this unimaginably early interval, the observable universe may have been compressed into conditions so extreme that quantum gravity dominated. Spacetime itself may have needed a quantum description. This does not mean the Planck era has been observed. It has not. It is not a hidden photograph at the back of the cosmic album. The Planck era is a boundary in our understanding. It marks the point where general relativity, which describes gravity and spacetime, must be combined with quantum theory, which describes matter, energy, uncertainty, and fields. After this unknown beginning, or unknown transition, the universe became more describable. One major idea about the very early universe is cosmic inflation. Inflation proposes that the universe underwent a burst of extremely rapid expansion in its earliest moments. Alan Guth, Andrei Linde, and Alexei Starobinsky are among the major figures associated with the development of inflationary theory. Inflation helps explain several features of the universe we observe today. It can explain why the universe looks so uniform on large scales, even in regions that seem too far apart to have exchanged signals in ordinary Big Bang expansion. It can help explain why space appears very close to flat on cosmic scales. It also provides a way for tiny quantum fluctuations in the early universe to become the seeds of galaxies and large-scale structure. Inflation is not the same as the Planck era, and it does not remove every mystery. Many versions of inflation begin after the Planck scale, when a classical space-time description is already becoming more usable. The exact beginning remains uncertain. Inflation may describe what happened very early, but not necessarily the deepest origin of space and time. The oldest light we can observe directly is the cosmic microwave background. This radiation was released about 380,000 years after the early hot state during a period called recombination. Before recombination, the universe was filled with a hot plasma of electrons and nuclei, and light scattered constantly from free electrons. Once the universe cooled enough for electrons to join with nuclei and form neutral atoms, light could travel freely. That ancient light still fills the universe today, stretched by cosmic expansion into microwave radiation. The cosmic microwave background is extraordinary, but it is not a view of the Planck era. It is a view of the universe much later, when the cosmos was already old compared with the Planck time. Still, it carries delicate patterns from earlier conditions. Those patterns have been measured with increasing precision by NASA's COBE mission, NASA's WMAP mission, and the European Space Agency's Planck mission. The Planck satellite, despite sharing a name with the Planck length, did not directly observe Planck scale physics. It measured the cosmic microwave background with great precision, helping cosmologists understand the age, composition, geometry, and early fluctuations of the universe. It gave a sharper picture of the ancient light, not a direct photograph of quantum gravity. The universe, as usual, keeps the most dramatic part just behind the curtain. The reason the early universe matters here is that it turns the smallest length into the largest question. At the Planck scale, distances are incredibly tiny, times are incredibly brief, and energies are incredibly high. These are exactly the conditions that may have shaped the earliest phase of cosmic history. If spacetime is continuous all the way down, the beginning may mean one thing. If spacetime is quantized, it may mean another. If the universe emerged from a previous contracting phase, as in some quantum bounce models, then the Big Bang might not be the beginning of everything, but a transition. If spacetime itself is emergent, then asking what happened before spacetime may be like asking what is north of the North Pole. Not necessarily meaningless as a sound, but perhaps not a question with the usual kind of answer. This is why understanding the Planck length matters so deeply. It is not just about tiny rulers and unimaginable decimals. It may be the key to understanding whether the universe began from a true first moment, rebounded from an earlier state, or emerged from a deeper quantum reality where space and time were not yet what they are now. The early universe was not merely small. It was a place where smallness, heat, density, gravity, and quantum uncertainty all became one problem. And somewhere near the Planck scale, the question of the smallest length quietly becomes the question of how everything began. The Planck length is often described as the smallest possible length, but that phrase can easily lead to the wrong picture. It can make space sound like a digital image made from tiny squares, each one the size of the Planck length. Zoom in far enough, the idea goes, and you would eventually see the pixels of reality. It is a wonderfully neat image. It is also not something physics has proven. The Planck length is a natural scale. It is built from the speed of light, Newton's gravitational constant, and the reduced Planck constant. It strongly suggests that our usual ideas about distance, measurement, gravity, and quantum mechanics all become tangled near that scale. But a natural scale is not the same thing as confirmed structure. It tells us where something important may happen. It does not automatically tell us exactly what that something is. There are several different possibilities. One possibility is that space-time is continuous, but that there is a minimum measurable length. In this view, space might not be made of discrete units. It may remain mathematically smooth in some deeper sense. But because measuring smaller and smaller distances requires higher and higher energy, and because energy gravitates, there may be a practical or fundamental limit to what can be resolved. Below the Planck length, the act of measurement may stop working in the familiar way. Another possibility is that spacetime really is discrete. In that case, the smoothness of space would be like the smoothness of a beach seen from far away. From a distance, sand looks continuous. Up close, it is grainy. Perhaps space-time is similar, appearing smooth at large scales, but having some deeper quantum structure at the Planck scale. But even here, caution is needed. Discrete space-time does not necessarily mean tiny cubes. Nature is not obliged to use graph paper. A universe made from little square blocks would be easy to draw, but it would also raise serious problems. It might introduce preferred directions, like the axes of a grid. Yet special relativity tells us that the laws of physics should look the same for observers moving at constant speeds relative to one another. This symmetry is called Lorentz invariance, and it has been tested with extraordinary precision. Any serious theory of discrete space-time must somehow preserve the success of Lorentz. invariants, or explain why any violations are too tiny to have been seen. This is not a minor detail. Lorentz invariance sits at the heart of special relativity. It is one reason the speed of light has the same value for all observers moving uniformly, and why space and time mix together into spacetime. If a theory of tiny spacetime grains carelessly breaks that symmetry, it risks damaging one of the best tested structures in physics. Loop quantum gravity offers one subtle kind of discreteness. It does not simply say that space is a grid of Planck-sized boxes. Instead, it suggests that geometric quantities such as area and volume can have discrete spectra. In quantum theory, a discrete spectrum means that only certain values are allowed. This is similar in spirit to the way an atom can have only certain energy levels. In loop quantum gravity, spin networks describe quantum states of geometry. These networks are relational structures, not little wires sitting inside ordinary space. They are part of the description of space itself. If this picture is correct, then smooth spacetime may emerge from many quantum geometric relationships, rather as the smooth behavior of a fluid emerges from countless molecules. But loop quantum gravity remains an active research program. It has not been directly confirmed by experiment. String theory offers a different possibility. In string theory, the fundamental objects are not point particles, but tiny one-dimensional strings. Because strings have extension, the idea of probing exact zero-size points can change. Some short-distance infinities that trouble point particle theories can be softened because interactions are spread out along extended objects. The smallest meaningful length might not arise because space is built from tiles, but because the basic objects used to describe nature are not exact points in the first place. Then there are approaches where space-time may be emergent. In these views, space and time may not be fundamental ingredients at all. They may arise from something deeper, such as quantum information, entanglement, or more abstract relationships. If that is true, asking whether space is continuous or discrete may be like asking whether temperature is smooth or grainy before understanding molecules. The question may need to be reframed. Causal set theory is another important approach. Developed by researchers including Raphael Sorkin, Luca Bombelli, Juhan Lee and David Meyer. Causal set theory proposes that space-time is built from discrete events ordered by causality. Instead of beginning with a smooth space-time manifold, it begins with a set of elementary events and the causal relationships between them. One event can be before another in the causal order, or unrelated to it if no signal could connect them. This is a very different kind of discreteness from a simple spatial grid. It puts causality first. Space and time, in the familiar continuous sense, are expected to emerge only at larger scales when many discrete causal elements are considered together. In this approach, the basic structure is not a tiny cube, but a network of possible before and after relationships. All of these ideas show why the Planck length must be treated carefully. It is not an automatic proof that space is made of little bricks. It is a clue that the classical picture of smooth, infinitely divisible space-time may be incomplete. It marks the place where quantum mechanics, gravity and relativity all insist on being heard at the same time. The safest answer is that we do not yet know whether space is actually discrete. It may be continuous with a minimum measurable length. It may be discrete in a subtle, quantum geometric way. It may involve extended strings. It may emerge from information or causality. Or the correct theory may use concepts we have not yet learned how to imagine. The Planck length strongly suggests that ordinary ideas of distance cannot be pushed downward forever without change. But it does not by itself prove that space is made of tiny cubes. Reality may have a grain, or it may have a deeper limit that is not grain-like at all, and that is the quiet beauty of the question. The smallest length reality allows may not be a final pixel. It may be the point where space stops behaving like something that can simply be divided, and begins behaving like something that must be understood in an entirely new way. Testing the Planck scale directly is far beyond present technology. The energies involved are so extreme that no existing particle accelerator can reach them, and no realistic near-future machine is expected to do so. The Planck length is not merely small, it is hidden behind an enormous experimental distance, a gap between what our theories can name and what our instruments can directly touch. But physics does not give up simply because nature has placed the answer somewhere inconvenient. It looks for clues. The challenge is that to probe shorter distances directly, one generally needs higher energies. The Planck energy is the energy scale associated with the Planck length, and it is vastly beyond what can be produced in particle collisions today. The Large Hadron Collider at the European Organisation for Nuclear Research, known as CERN, is an extraordinary machine, but even it operates many orders of magnitude below the Planck energy. Building a collider that could directly reach the Planck scale would not be like building a slightly larger tunnel. It would be more like asking engineering to politely become magic. So scientists search for indirect evidence. The idea is that some tiny effect from quantum gravity might be too small to detect in a laboratory, but might accumulate over enormous distances or appear in extreme cosmic environments. The universe itself becomes the experiment. Instead of trying to build a Planck-scale machine on Earth, physicists use light, particles, gravitational waves, and ancient cosmic messengers that have travelled across space for billions of years. One possible clue involves the speed of light. In special relativity, the speed of light in a vacuum is the same for all observers moving at constant speeds, and it does not depend on the energy of the light. This is part of Lorentz invariance, one of the core symmetries of modern physics. Some speculative quantum gravity ideas suggest that Lorentz invariance might be very slightly modified at extremely high energies. If so, photons of different energies might travel at slightly different speeds through space. The effect, if it exists, would be tiny. Over a short distance, it would be hopelessly small. But over billions of light years, even a minute difference might build up into a detectable delay. This is why gamma-ray bursts are useful. Gamma-ray bursts are among the most energetic explosions in the universe, often associated with collapsing massive stars or merging compact objects. They release bursts of high-energy light that can travel across cosmic distances before reaching our detectors. The Fermi Gamma Ray Space Telescope has been used to test whether high-energy photons from distant gamma-ray bursts arrive later or earlier than lower-energy photons in a way that would suggest a breakdown of ordinary relativity. So far, observations have found no confirmed violation of Lorentz invariance. That absence matters. It places strong limits on theories that predict energy-dependent light speed at levels large enough to be observed. High-energy cosmic rays offer another possible window. Cosmic rays are energetic particles, mostly protons and atomic nuclei, arriving from space. Some carry energies far beyond anything produced in human accelerators. The Pierre Auger Observatory in Argentina studies ultra-high-energy cosmic rays by observing the particle showers they create when they strike Earth's atmosphere. These events may carry clues about extreme astrophysical processes, and they can also test whether particle behavior at very high energies matches known physics. Neutrinos are another messenger. They're extremely light particles that interact only weakly with matter, which means they can travel through stars, galaxies, and even Earth with remarkable ease. The Ice Cube Neutrino Observatory, buried in Antarctic ice, detects flashes of light produced when neutrinos interact near its detectors. High-energy neutrinos can test particle physics and astrophysics across enormous distances. They may also help constrain exotic ideas about space-time propagation or quantum gravity effects. The Cherenkov Telescope Array is designed to study very high-energy gamma rays from cosmic sources using ground-based telescopes. When gamma rays strike the atmosphere, they produce cascades of particles that emit brief flashes of Cherenkov light. Observing these flashes allows scientists to study extreme objects such as supernova remnants, active galactic nuclei, and possibly signals relevant to fundamental physics. Gravitational waves provide another kind of test: the laser interferometer. Gravitational Wave Observatory, known as LIGO, along with Virgo and Cagra, detects ripples in spacetime from events such as merging black holes and neutron stars. These observatories do not directly measure the Planck length. Their arms are kilometers long, and the waves they detect come from huge astrophysical systems. But they test general relativity in extreme conditions, where spacetime is strongly curved and moving violently. So far, gravitational wave observations have agreed very well with Einstein's theory. The waves travel at speeds consistent with the speed of light to extraordinary precision, especially after the neutron star merger observed in 2017, which was accompanied by electromagnetic signals. This strongly constrains many alternative theories of gravity. Again, the non-detection of deviations is not a disappointment. It is information. This is an important part of good science. A discovery can be exciting, but so can a careful non-discovery. If a theory predicts an effect that should be visible and observations do not find it, then that theory may need to be revised, restricted, or abandoned. Nature's silence can be surprisingly talkative. The Planck scale remains hidden, but not completely beyond investigation. Scientists cannot yet place a detector at 1.6 times 10 to the minus 35 meters and watch spacetime behave. But they can test whether the consequences of Planck scale ideas leak upward into observable physics. They can look for tiny violations of Lorentz invariance, unusual particle propagation, modified dispersion relations, changes in gravitational wave behavior, or unexpected signals from high-energy astrophysical messengers. So far, the central lesson is caution. No confirmed experimental evidence has shown that spacetime is discrete, that light speed depends on energy in vacuum, or that quantum gravity has visibly altered the cosmic signals we have measured. This does not mean quantum gravity is unnecessary. Black holes, singularities, and the early universe still demand a deeper theory. It means that any correct theory must be subtle enough to agree with the extraordinary success of known physics across all tested scales. The Planck length remains a boundary of direct measurement, but not a boundary of scientific imagination. The universe may already be carrying hints from that scale in ancient light, violent collisions, ghostly neutrinos, and ripples in space-time. The difficulty is learning how to listen without hearing patterns that are not really there. For now, experiment has not opened the Planck scale, but it has narrowed the paths toward it. And sometimes, in science, ruling out the wrong roads is how the right road slowly begins to appear. The idea of a minimum length appears in several different routes toward quantum gravity. It is not owned by one theory, and it does not have one single agreed meaning. Sometimes it means a smallest measurable distance. Sometimes it means a shortest physical wavelength. Sometimes it means a limit beyond which the familiar idea of localization stops improving. In every case, it points toward the same quiet suspicion. Perhaps nature does not allow distance to be sharpened without end. In ordinary quantum mechanics, the closest familiar idea is Heisenberg's uncertainty principle. Werner Heisenberg showed that certain pairs of physical quantities cannot both be known with unlimited precision. The most famous pair is position and momentum. If a particle's position was made more precise, its momentum becomes less precise. If its momentum is made more precise, its position becomes more spread out. This is not because the particle is hiding its details from us in a tiny cupboard. It is not a problem of clumsy measuring devices. It is built into the mathematical structure of quantum theory. The wave function that describes a quantum system cannot be squeezed in position without spreading in momentum. This is standard quantum mechanics, and it has been tested across an enormous range of experiments. But some physicists have wondered whether quantum gravity might modify this principle at extremely small scales. The proposed idea is often called the generalized uncertainty principle. It is not one single formula accepted by everyone, but a family of related ideas appearing in a string theory, black hole thought experiments, and quantum gravity-inspired models. The basic thought is this. In standard quantum mechanics, making position more precise requires larger uncertainty in momentum. Larger momentum means higher energy. Normally, that is not a problem for the structure of space-time itself, but near the Planck scale, enough energy concentrated into a tiny region can no longer ignore gravity. The energy used to localize the particle may begin to curve space-time, or even create conditions related to black hole formation. So the usual uncertainty relation may not be the whole story. A generalized uncertainty principle can suggest that beyond a certain point, adding more energy no longer gives a better measurement of position. Instead of resolving a smaller region, the extra energy may increase gravitational disturbance. The measurement stops sharpening. It begins to blur. In ordinary terms, it is a little like trying to inspect dust on a table with a brighter and brighter lamp, until the lamp becomes so intense that it burns the table. More light no longer helps. It changes the thing you were trying to see. Near the Planck scale, the problem is not a hot lamp, but the gravitational effect of concentrated energy on spacetime itself. David Gross and Paul Mende explored minimum length ideas in the context of high-energy string scattering, where string theory suggested that attempts to probe very short distances may behave differently from point particle expectations. Michel Maggiore and other researchers have studied generalized uncertainty principles and their possible connections to quantum gravity, black holes, and Planck scale physics. These ideas are not fringe curiosities. They are serious attempts to understand what happens when quantum mechanics and gravity are forced into the same tiny room. Still, it is important to distinguish this from ordinary uncertainty. The usual Heisenberg uncertainty principle does not by itself prove a minimum length. It limits how precisely position and momentum can be known together, but it does not say there is a smallest possible position uncertainty in all circumstances. In standard quantum mechanics, one can write wave functions that are localized more and more tightly, as long as one accepts greater and greater momentum uncertainty. A generalized uncertainty principle goes further. It proposes that once gravitational effects are included, there may be a non-zero minimum position uncertainty. That would mean there is a smallest localization scale in a deeper theory. You could try to squeeze a particle's position more tightly, but the attempt would stop improving the result. The universe would not simply say no with a little stamp on the paperwork, but the physics would no longer allow the usual concept of sharper location to continue. This connects naturally to the Planck length. The proposed minimum length is often expected to be close to the Planck scale, because that is where the reduced Planck constant, Newton's gravitational constant, and the speed of light combine. It is the place where quantum behavior, gravity, and relativity all become relevant at once. Another related idea is doubly special relativity. Giovanni Amelino Camelia, Juanma Geijo, and Lee Smolin are among the physicists associated with its development. Ordinary special relativity makes the speed of light an invariant quantity, meaning all observers moving at constant speeds agree on it. Doubly special relativity explores the possibility that there may be a second invariant scale as well, often connected to the Planck length or Planck energy. This is a delicate idea, because special relativity is extremely well tested. Any modification must preserve the known successes of Lorentz invariants, or reproduce them so accurately that experiments still agree with Einstein's theory at ordinary energies. Doubly special relativity is an attempt to ask whether a Planck scale limit can be built into relativity without simply breaking the theory. These proposals remain speculative. No experiment has confirmed a generalized uncertainty principle. No observation has shown that doubly special relativity is the correct description of nature. No laboratory has measured a universal minimum length. The mathematics is intriguing, and the concepts are powerful, but physics asks for evidence as well as elegance. Even so, minimum length ideas matter, because they sharpen the central question. The Planck length may not be a tiny object. It may not be the side of a cosmic pixel. It may instead be the scale where localization, measurement, energy, and gravity stop behaving as separate ideas. In that sense, the minimum length is less like a wall at the end of a corridor, and more like the point where the corridor ceases to be the right image. You can keep writing smaller numbers in mathematics, but physical measurement may no longer follow. Below a certain scale, nature may not provide sharper locations, only deeper relationships. The smallest length reality allows may therefore be a limit not only on space, but on precision itself. It asks whether the universe can be divided forever in practice, or whether the act of division eventually awakens the full machinery of quantum gravity. And if it does, then the Planck length is not just a small distance. It is the place where the simple question, where exactly, begins to dissolve. Perhaps the strangest possibility is that length is not fundamental at all. The Planck length may not be the size of the smallest object, or the width of a tiny grain of space, or the side of a hidden cosmic tile. It may be a sign that below a certain scale, the very idea of distance stops being the deepest language available. This is the idea of emergent spacetime. In physics, something is emergent when it appears at a larger scale from many smaller ingredients that do not individually possess the same property in a simple way. Temperature is a familiar example. A single molecule does not really have a temperature in the ordinary sense. Temperature emerges from the average motion of many molecules together. When countless particles move, collide, and exchange energy, the large-scale concept of heat becomes meaningful. The analogy is not perfect, because space-time is far deeper than the warmth of a cup of tea. Still, it is useful. It shows how a familiar property can be real without being fundamental. Temperature is not fake simply because it emerges from molecular motion. It burns your tongue quite convincingly if you rush the tea. But its deepest explanation lies beneath the everyday concept. Space-time may be similar. Space and time might be real at the scales where we live, measure, travel, and observe. They may still be excellent descriptions of reality. But perhaps they arise from something more basic: quantum relationships, information, entanglement, or structures that are not spatial in the usual sense. Entanglement is one of the key ideas here. In quantum mechanics, entangled systems have linked properties even when separated by large distances. Albert Einstein, Boris Podolsky, and Nathan Rosen famously challenged quantum mechanics in 1935, arguing that it seemed incomplete if it allowed such strange connections. Einstein disliked the idea so much that he referred to it as spooky action at a distance. John Bell later showed that this debate could be turned into experimental tests. Bell's theorem demonstrated that certain predictions of quantum mechanics differ from any theory based on simple local hidden variables. Experiments by Alain Aspect and others showed results consistent with quantum mechanics. Later, quantum information research has made entanglement not just a philosophical puzzle, but a practical and mathematical resource. What does this have to do with space? Some modern ideas suggest that space-time geometry may be connected to patterns of entanglement. In ordinary thinking, we imagine two objects as entangled despite being separated by space. But perhaps, in a deeper theory, the pattern of entanglement helps create the sense of spatial connection in the first place. Space may not merely contain entanglement. Space may partly emerge from it. Mark van Raamsdonk is one physicist strongly associated with this idea. He argued that changing the entanglement between parts of a quantum system can be related to changing the connectivity of space-time. In a memorable sense, entanglement may help stitch space together. Reduce entanglement enough, and connected regions of space-time may begin to separate. This idea becomes especially powerful in the anti-de Sitter conformal field theory correspondence, introduced by Juan Maldacena in 1997. In this correspondence, a theory with gravity in a higher dimensional anti-de Sitter spacetime can be equivalent to a quantum field theory, without gravity on its lower dimensional boundary. The gravitational world inside can be described by quantum information on the boundary. This does not mean our universe has been proven to work exactly this way. Anti-de Sitter space is not the simple large-scale geometry of our own universe, but the correspondence gives a precise example where space-time geometry and quantum information are deeply linked. It suggests that geometry may not be the starting point. It may be something reconstructed from a more fundamental quantum description. Tensor networks offer another useful bridge. A tensor network is a mathematical structure that organizes entanglement in complex quantum systems. Brian Swingle and other researchers have explored connections between tensor networks and emergent geometry, especially in the context of holography. Certain tensor network patterns can resemble spatial geometry, suggesting that the shape of space might arise from patterns of quantum entanglement. Again, this is not a finished answer, it is a clue. But it is an important clue because it changes the question. Instead of asking whether space is smooth or grainy, continuous or discrete, we may need to ask why space appears at all. The deepest theory may not begin with little distances. It may begin with relationships, information and quantum states, from which distance emerges only later. If space-time is emergent, then the Planck length may mark a boundary where the emergent description breaks down. It would be like trying to ask for the temperature of one molecule. The question is not exactly forbidden, but it may be using a large-scale concept where it no longer applies cleanly. Below a certain level, temperature gives way to molecular motion. Below a certain level, length may give way to quantum information. This possibility is both humbling and strangely elegant. It suggests that the smallest length reality allows may not be a tiniest measurable object hiding beneath all others. It may be the point where length stops being the right thing to look for. At ordinary scales, space-time feels obvious. Things are near or far. Events happen before or after. Light travels across distances. Planets move through curved geometry. But near the Planck scale, perhaps these familiar ideas are not the foundation. Perhaps they are the surface. The universe may not be built inside space in the way we imagine. Space itself may be built from something deeper, and if that is true, then the Planck length is not the final grain of reality. It is the place where the language of grains, distances, and locations begins to fade, and a quieter language of quantum connection waits underneath. After travelling through Planck lengths, black holes, quantum gravity, and the possibility that space itself may not be fundamental, it might sound as though smooth space-time should be thrown away entirely. But that would be a mistake. A very understandable mistake, perhaps, but still a mistake. Smooth space-time remains one of the most successful ideas in the history of science. General relativity treats space-time as a smooth, curved structure. Mass and energy shape it. Objects move through it along the straightest possible paths available in that curved geometry. This picture is not just elegant, it works. It has been tested again and again across planets, clocks, stars, galaxies, black holes and gravitational waves. One of the earliest great tests came in 1919 during the Eddington Eclipse expedition. Arthur Eddington and his colleagues measured the positions of stars near the Sun during a solar eclipse. Einstein's general relativity predicted that the Sun's gravity would bend starlight by a specific amount. The observation supported Einstein's prediction and helped make general relativity famous around the world. It was one of those rare scientific moments where a difficult geometric theory briefly became headline news, which is not something geometry usually expects from life. General relativity also explains the orbit of Mercury. In Newtonian gravity, Mercury's orbit almost works, but not quite. The closest point of Mercury's orbit around the Sun shifts over time in a way that Newton's theory could not fully account for. Einstein's curved space-time explained the remaining difference. The planet was not misbehaving. It was simply moving through geometry more subtle than Newton had known. Then there is gravitational time dilation. In general relativity, clocks run at different rates depending on gravitational potential. A clock deeper in a gravitational field ticks more slowly than one higher up. This has been tested directly. The Hafele-Keating atomic clock experiment in the 1970s flew atomic clocks around the world on commercial aircraft and compared them with clocks left on the ground. The results matched the combined predictions of special relativity and general relativity. The same principle is not just a laboratory curiosity, it is built into modern technology. Global Positioning System satellites carry precise atomic clocks, and those clocks experience time differently from clocks on Earth's surface because of both their motion and their altitude in Earth's gravitational field. Without relativistic corrections, GPS positions would drift by kilometers over time. So every time a phone manages to guide someone to a coffee shop with suspicious confidence, it is quietly using Einstein. General relativity also predicted black holes long before we had direct observational evidence for them. Today, black holes are central to astrophysics. The Event Horizon Telescope collaboration has imaged the shadow regions around supermassive black holes, including the object in the galaxy Messier 87 and Sagittarius, a star at the centre of the Milky Way. These images do not show the event horizon itself as a solid surface, but they reveal the behaviour of light and matter in the strong gravity near black holes. And in 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves. These ripples in space-time came from the merger of two black holes. The signal matched the predictions of general relativity with remarkable precision. Since then, LIGO, along with Virgo and Kagra, has opened an entirely new way of observing the universe through space-time vibrations rather than light. General relativity also helps describe the expansion of the universe. Cosmology depends on Einstein's equations to model how space evolves over time under the influence of matter, radiation, dark matter, and dark energy. The fact that the universe expands, that galaxies recede, and that space-time itself has a cosmic history all fit within this smooth relativistic framework. So if Planck-scale physics may eventually replace smooth space-time at the deepest level, why do we still use smooth space-time at all? The answer is that physics often works through effective theories. An effective theory is a description that is accurate within a certain range, even if it is not the final, deepest description of reality. It does not have to know everything in order to be extremely useful. It only has to capture the right behaviour at the scale where it is being applied. Water is a good example. At everyday scales, water is a smooth fluid. It flows, forms waves, fills containers, and carries boats. We can describe it with fluid equations without tracking every molecule. But water is not fundamentally smooth. It is made of molecules. If we zoom in far enough, the smooth fluid picture gives way to molecular motion. That does not make the fluid picture fake. It makes it effective. Smooth space-time may be similar. At large scales, it works beautifully. It describes planets, stars, clocks, light and gravitational waves. At the Planck scale, it may give way to something deeper. Quantum geometry, strings, causal sets, entanglement, or some theory not yet imagined clearly. But the success of the deeper theory would still have to explain why smooth space-time emerges so accurately at larger scales. Kenneth Wilson helped develop renormalization group ideas, which show how physics at one scale can become largely independent of unknown details at much smaller scales. This is one reason science can make progress without already knowing the final theory of everything. The behaviour of a gas does not require every quantum detail of its atoms. The orbit of Mars does not require knowing the structure of space-time at the Planck length. This is the balance worth holding on to. The Planck length matters deeply. It may reveal where smooth space-time stops being fundamental. It may point toward quantum gravity, minimum length, or emergent geometry. But it does not make ordinary space unreal. It does not make general relativity fragile. It does not mean the floor beneath you is secretly unreliable, although floors can still betray people in socks. Smooth spacetime remains one of the best descriptions we have ever found. It may not be the final layer of reality, but it is real in the way effective truths are real. It is the large-scale language of gravity, motion, time, and cosmic structure. The Planck length does not destroy that language. It simply tells us that, at the smallest scales, another language may be waiting underneath. A length seems like one of the simplest things in the world. It is the distance from here to there, the gap between two marks, the width of a table, the height of a door, the space between stars. We use length so naturally that it feels almost too obvious to question. But at the Planck scale, even this simple idea becomes difficult. In physics, a quantity is meaningful when it can be connected, at least in principle, to measurement, prediction, or physical relationships. This is sometimes called operational meaning. A length is not only a number written on a page, it is something that can be compared with a ruler, crossed by light, inferred from motion, measured with instruments, or used in a theory to predict what nature will do. At ordinary scales, this causes no trouble. A meter can be measured. A kilometre can be travelled. The distance to the moon can be found by bouncing laser pulses from reflectors left by Apollo astronauts. The distance to nearby stars can be measured through parallax, and larger cosmic distances can be estimated through standard candles, redshift, and other astronomical methods. These distances are not just mathematical possibilities, they are tied to physical procedures. Mathematics, however, can go further than measurement. A line can be divided in half forever. Between any 2 points, no matter how close, another point can be imagined. Euclidean geometry and calculus allow this without complaint. Ideal points have no size. Distances can shrink towards zero. The mathematical page remains calm, even while physics begins to look slightly nervous. The question is whether nature allows every mathematically possible distance to have physical meaning. Can a distance smaller than the Planck length be measured, probed, or used in an experiment? Or does the phrase "a smaller distance" eventually stop meaning what it means in ordinary space? The black hole measurement problem suggests one possible limit. To examine a smaller distance, we need higher energy. But energy gravitates. If enough energy is compressed into a tiny enough region, general relativity says an event horizon may form. Instead of revealing finer structure, the measurement could hide the region behind a black hole. The attempt to look more closely would defeat itself, which is a little rude, but very much in character for extreme physics. Quantum uncertainty points in the same direction. To localize a particle more tightly, its momentum uncertainty increases. Greater momentum means greater energy. At familiar scales, this is simply quantum mechanics doing its usual strange but reliable work. Near the Planck length, however, that energy may make gravity unavoidable. Position, momentum, energy, and space-time geometry can no longer be treated as separate concerns. Space-time foam offers another image. John Archibald Wheeler suggested that at the smallest scales, geometry itself might fluctuate. If space-time is quantum, then distances and durations may not remain sharply defined in the smooth classical way. The Planck length would not be a little dot, but a region where the idea of a precise geometric separation begins to blur. Other approaches offer different possibilities. Loop quantum gravity suggests that area and volume may have discrete spectra, so geometry could have quantum structure. String theory suggests that fundamental objects may be extended rather than point-like, changing what very short distances mean. Causal set theory imagines space-time arising from discrete events, ordered by causality. Holography suggests that gravitational information may be counted on boundaries in units related to Planck area. Emergent space-time goes even further, suggesting that length itself may arise from deeper quantum information or entanglement. These ideas do not all say the same thing. They may not all be right. Some may be partly right, some may be wrong, and the final answer may be stranger than any of them. But they all circle the same boundary, the point where classical distance stops being simple That is why the Planck length must be treated carefully. It is not proven to be a literal minimum length. It is not confirmed as the size of a physical pixel. It is not known to be a tiny brick from which the universe is built. Physics does not yet know whether it represents an exact lower limit, an approximate measurement boundary, or a signpost toward concepts deeper than length. What we can say is more cautious and more interesting. The Planck length is the scale where quantum mechanics, gravity and relativity all become relevant at once. It is the scale where trying to define a smaller distance may require a theory we do not yet possess. It is where the smooth map of space-time reaches the edge of its reliable territory. So the smallest length reality allows maybe less like a final brick and more like the edge of the map. Beyond it, there may not be smaller and smaller places in the ordinary sense. There may be quantum geometry, hidden strings, causal relations, entanglement, information, or something no current picture fully captures. Distance begins as a simple question. How far is it from here to there? But at the Planck scale, here and there may no longer be basic ingredients. They may be large-scale ideas, useful and real above the boundary, but not fundamental beneath it. And that may be the quiet truth at the heart of the smallest length. Reality may not end in a smaller thing, but in a deeper meaning. The smallest length reality allows is, for now, the Planck length. The smallest length our current best ideas can sensibly point toward. But it is not a confirmed physical pixel of space. It is not known to be a tiny brick at the bottom of everything. It is a real and well-defined natural scale, yet the exact nature of space-time there remains unknown. We began with classical smooth space, with Isaac Newton's absolute stage and Euclid's clean geometry, where distance can be divided without end. We move through measurement, where rulers, light, particles, clocks, and instruments make length physical rather than merely mathematical. Then came Max Planck's quantum constant, Einstein's relativity, Hermann Minkowski's spacetime, and Werner Heisenberg's uncertainty, each one quietly weakening the old idea that smaller always means simpler. Black holes showed us why measuring too closely may hide rather than reveal. Planck time showed that the smallest distance is also tied to the smallest duration we can sensibly name. Quantum gravity revealed the missing theory beneath the whole question. Wheeler's space-time foam, loop quantum gravity, string theory, holography, black hole entropy, the early universe, experimental limits, and emergent space-time all pointed toward the same quiet boundary. That boundary does not weaken physics. It strengthens it. It shows where current physics is honest enough to stop pretending it already knows. Reality may not allow smaller measurable lengths in the ordinary sense, or it may allow them only in a deeper language we have not yet learned. Quantum geometry, strings, causal relations, information, or something stranger still. Every familiar distance from the width of a hand to the span of the observable universe may rest above this hidden edge where space, time, energy, and information meet. The Planck length is not merely a tiny number. It is the soft edge of our map, where the universe seems to ask for a new language.